Mic higher, mic lower? Sound all right? Okay. Folks that just walked in, I designed this as a play-along. If you have a laptop, you can kind of twiddle along while I'm talking. If you don't, it'll probably make it, I'll probably be able to cover more information. But if you're interested, I have a thumb drive with the dev kit that I'm using up here loaded up. If people want to try it out for any, Mac, Windows, Debian. I didn't test much farther than Debian on the Linux side, but the pieces are there. I didn't throw an IDE on here. I figure most people have a text editor. Yeah, if you're using Emacs, you're teaching the rest of this because you're already over my... or V, yeah. But it's here if you want it. I can pass it around. Or... Is it the same as the file? It is, yeah. If you can get internet, that's even better. And all three operating systems are packed in one. I'll give another couple minutes, huh? A little early. I don't know if my watch is right. As a preview, having prepared for weeks, we'll be lucky to get any pixels on the screen in 1 hour of coding. But I have a lot prepped, so if people aren't following along, I can kind of jump through the code a little faster. Out of curiosity, just to get a sense of audience, how many people in here have programmed anything? Awesome, step in the right direction. How many people in here have programmed in an assembly language? All right, I don't need to be here today. How many people have done 6502? All right, I barely need to teach this, we're good. So really all I have to teach you about is the NTSC signal. How many people have programmed on Atari already? Tried, okay, that's all right, yeah. Yeah, that's about where we're at with it. Yeah, it's a tough beast. Okay, that helps me out, so. It is all about counting, yeah. You guys can give me the go-ahead. I don't know if my clock is right. Oh, we're running? Oh, okay. Oh, okay. Hey, easy enough then. All right. So my name's Will Lindsay. I am a what do I do? I teach game design at Rider University. Started a program there a couple years ago. I've been teaching game design and interactive media for 11 or 12 years. I am an artist by trade. So I do not remotely have anything related to an engineering background. I think that gives me an advantage as a teacher because I learn code empirically and I teach code empirically. So I mess up, I make mistakes, I try over, start over again. And it works pretty well. And for the younger set, for my students, it keeps them engaged. And it works pretty well, as long as we can get a picture on the screen. I have been trying for a few years to teach 2600 programming in that venue, and I'm not quite there yet. But you guys might be able to grasp it here. The last VCF, I did a talk on chip 8, and that's been my weapon of choice for teaching retro computing. It's kind of a toy language, so it gives you the very, very, very beginnings of assembly language, which is scary enough for students who are coming from upper level languages or no languages at all. So let me talk about the Atari for a minute. Let's see. So there it is. There's an Atari 2600, and we all know that one. And it was designed initially to do, bear with me here. Geez, where did I put all my pictures? This was the goal when they designed this thing. That's the kind of graphics they were hoping for, right? And in fact, the entire system was designed around the games that were known at the time, which was pretty much Tank and Pong. And so when they designed this thing, they pretty much thought it would be a universal machine that could play lots of versions of Tank and Pong. And because of that, the graphics and the way the system was designed is designed to do exactly that. And as an example, and I'll get a little deeper into it later on, there are various registers, there are various areas in memory that are designed to make it a little easier for a game programmer to get graphics on the screen. And the things that they thought every game designer would need at this point was there would be 2 players, and each player would have 1 bullet, so tanks and tank bullets, a background, a background color, I should say, and then a background with some shapes that could, may or may not be part of the game, and a ball, just in case you were playing Pong. And that was it. So it worked. It worked really well for this. And compared to other things that were on the market at the time, I think things worked out. Within a couple of years, programmers got much sharper than the original designers. And they did some amazing things on this machine, and that's part of why this machine has kept me fascinated for so many years. Looking at that and knowing that they're still only dealing with 2 player sprites, 2 bullet sprites, a ball sprite, and then 1 background color. There's some amazing things happening here in programming. So people came a long way in a very short amount of time. We're not remotely going to get here today. But I can kind of talk about the basics and how people started to move in that direction. So I have a sense that some people in the room are from asking previously, so there's some knowledge of assembly language and 6502 programming. So to talk about the Atari for a second, the Atari, whoops, you guys are going to need to share files. We'll throw that back up. So the processor in here was a 6507. That is a chopped down, hacked, cheap version of the 6502. The language is the same, which is awesome. So it made it transferable. It made it an easy skill to learn this new machine for most people. It's hacked down in the sense that it only addresses a very tiny section of memory that the 6502 was capable of. There's some other changes that were made to the chip to make it cheaper. One of them is that there's no interrupt pins on the chip, which is strange. Anybody who's dealt with video game design or games in general, for many, many, many years, interrupts were kind of the heart of what we do. If the player pushes a fire button and they don't see a bullet on the screen, they're bored already, right? So that immediate gratification has to be there. But there were ways to work around that in here, and I think they did a pretty good job at it. These controllers are kind of interesting. My students have barely seen anything like this, which is kind of interesting. So a little bit of history and understanding that one. Again, coming from Tank, and I think the original joysticks were derivative of maybe actual tanks, where you would have 2 joysticks, or at least something similar to that. The idea was nice. I know most people my age had carpal tunnel by the age of 7. It's not quite ergonomically friendly. It does up, down, left, right, and fire. It goes through a regular 9-pin serial, so we could squeeze a little more in there if we had to, but in general, they didn't design it to be that way. The processor can handle parallel inputs, which means you could theoretically fire and move at the same time, theoretically, at least fast enough that we don't notice it as people. So this is what folks had to work with. And let me start talking about how they did it. I'm going to pull up a memory map real quick. This isn't a real memory map. And of course, the font's way too small. Bear with me. Obviously not a real memory map, but it's enough to get us going. So besides the 6502, there's another chip in there the television interface adapter, TIA chip, and all of the different chips had slang names. There's also something called the Riot chip, which basically handled in and out, input, output, and timers. Very, very limited. So what are we looking at? 128 bytes of RAM. 128 bytes of RAM. So the picture of the Atari that I just had up there is a little bigger than that, to kind of give you a sense of that, yeah. The screen, let me pull up one of those again. I'll pull up Combat again. We can't really think in pixels, but if we were thinking in pixels because we're digital folks, this screen is 160 by 192. The 192 has to do with scan lines on an American television back in the 70s and 80s using the NTSC format. A lot of that space is wasted space, so we're not really seeing the full picture of it. Very, very low resolution. I'm giving another talk on Sunday specifically about the game Adventure and how that was adapted from text games at the time. And one of the things that I always think is a miracle is the fact that you can get anything to even look recognizable with this amount of pixels. So that is definitely part of the charm and troubles with the 2600, with the Atari. I'm skipping all over the place. Unlike almost every machine that came after this, almost every game machine after this had a video buffer. It had a space in memory that was big enough to hold everything or most of everything that was on the screen. This did not. And this is one of the things that makes this such a challenging machine. So in the NTSC signal, just to give a gist on old-fashioned tube televisions, which most of the people in this room remember, right? There is a little, to put it in plain English, there's a little gun that's going back and forth that's spraying a beam against the front of the TV, and there's some phosphorus up there that's giving us some persistence of light so that we actually see an image on the screen. And the signal requires that the beam go side to side at a certain speed, cover the whole screen at a certain rate, and then return and do it again. On the Atari 2600, the processor had to manage that. The code had to manage that, which means the programmer had to know exactly where that beam was at any given moment. And occasionally you hear this phrase, racing the beam. And it's literally this idea that if you wanted to put a dot on the screen, you had to be there in the code before the NTSC signal got there, before the beam got there, and then drop it in the spot. So perfectly timed coding. There were a couple little tricks in there that help us, not many. For the most part, that's what Atari code does, is it just chases this beam around the screen. There is some space. Let's see, did I bring this one? No, I just brought the manual. I'll find it in the manual real quick. Bear with me. You can tell I teach in a college. I'm like half prepared, right? And inevitably, somebody asks me a question, I get completely off track. Okay, so some of you have seen this before. This is a fairly well-known, diagram in the Atari world. This So 282 scan lines on the NTSC signal. Out of that, we actually only see, or most televisions only saw 192 of these. So this little slice in here. There's different reasons that this happened to my understanding. One of them is that television manufacturers didn't originally completely agree on this. And so there was some space around the image that sometimes was needed on some TVs, and sometimes you had a nice wood grain plasticky bezel that ran around the TV that covered it. But we could count on that 192 scan lines being useful picture. You'll notice in the emulator that I'm using, I have other space above it and below it. And this is the vertical blank and an overscan. So the vertical blank, it's kind of weird. It's not actual scan lines in a sense. And the horizontal blank, the same thing. There had to be a little bit of time, and we're talking about microseconds here. There had to be a little bit of time when the beam was at the top or bottom of the screen to get back to where it was supposed to be. So it would literally fly back and then turn off, fly back, and then start shooting its beam again. And the amount of time that took is this vertical blank. And then same thing as it crossed the screen from one side to the other, it would fly back, and we'd have a little bit of time in there that we weren't drawing pixels, that we could slip a little code in there, which is really nice. That's the horizontal blank. So you have 192 horizontal blanks. Everything about the game, the reading the joysticks, the input, scoring, figuring out if things collided into each other, anything that had to do with the interaction of the game, or keeping track of things had to happen in those two blanks. There were occasionally a couple little tricks to slide things onto the screen, and folks probably have a vivid memory of playing games where occasionally there were little black lines that would pop up on the left-hand side. And sometimes that was the programmer cheating it a little bit and saying, I'm going to use some of this. Nobody will notice, I swear. It's not a lot of time, frankly. I'm going to pop open some code and jump into it. I think that's enough. If anybody's playing with the file that I gave them, or if anybody online is playing with the file I gave them, we use a compiler called DASM, which is a 6502 compiler that happens to also do 6507. I am currently using an emulator called Stella. Anybody who's played anything Atari related on a PC or Windows or Mac is probably familiar with that one already. It's really accurate. I'm really pleased with it. It's open source. They've been doing a good job on it. Nowadays, things are a little bit easier. We've got some cheat files to get us going in the right direction. I've included those. So these header files, VCS header, macro header, take care of some shortcuts for us. One is there are a whole bunch of address spaces on the TIA that had these lovely nicknames like COLUP0, color luminance for player 0, these little reminders of what those addresses in memory were supposed to do. One of these header files kind of takes care of that for us, so we can address them the way that they were written in the original manual in 1979. Unbelievable there's a manual for this thing, and it's still hard to program. Macros do things for us, like if I lose count of lines, I could just sleep the processor, just shut it down for a little bit so that the NTSC signal can catch up to me. And that happens for various reasons. I already showed you the memory map, so I'm not going to get into this too much, but basically this is my RAM space, so I could throw a little variable in there if I wanted. And then this is where the code begins for every cartridge. All the way down at the bottom, this little bit, which seems weird to folks, is to guarantee that my compiled ROM packs into that 4K exactly. If it's a little off, I don't know what would happen, to be honest. I haven't tried it. But so it basically, this helps pad it with blank space. This is an odd one. I don't know where this convention came about, and maybe somebody can teach me a little bit later today. But this isn't even used. We're literally just using that to fill 16 bytes to make sure we have exactly the right space on there. So let's get into the code. There's a nice little macro in here, clean start, that I'm using. And again, anybody who's programmed in the last 20 years for an Atari is using these header files. So there's some things that made it a little bit easier for us. That basically starts the Atari in a known state. If we have everything in a known state, if we know that the variables are all zeroed out, or I'm sorry, the RAM's all zeroed out, that the registers are where they should be, it makes things a lot easier. A lot of the registers in the Atari are latched, meaning when you write to them, they stick. So if I want to put the color blue into the background, I don't have to continually write the color blue to that register. I do it once and it sticks there. The problem with that is if I do a fast reset on the machine, and I'm sure every little kid did this in the 70s, you sit there and play with that reset button until it just glitches out, right? And what's actually happening is there's spaces in memory that are still filled from the previous program and not doing quite what we want to. So this clears it out for us. And then I have this chunk of code starting at new frame right here. And this guy goes the whole way down to here, jump new frame, and the entire game happens in this continuous loop, and that loop is drawing one frame onto the screen. That's all it does. And everything else has to be squeezed in between the lines that I have up here. There are dozens of different approaches to doing this, and there's ways that you can cheat some of this timing. But I created a dirty way of doing this, or we're looking at a dirty way of doing this, so that it's easy to understand for somebody who's new to this. So remembering this guy right here, we have a vertical blank. There's actually this little section of code right here. I should be pointing at the screen. There's this little section right here called vertical sync. That has to be 3 scan lines. It basically tells the TV to get ready. Here comes the picture, right? And then the vertical blank. And then we have the actual picture in here, and then some overscan, which showed up on some TVs and didn't show up on others, so we don't use it. And the same thing is happening in my code here. So here's my vertical sync. And again, this was a nice macro that takes care of that 3 lines for us. Frankly, I could have written 3 lines that sync, but I got used to using it. This little chunk of code right here, so I'm loading 37, and I'm going to speak very lightly about the code since I know not everyone in here codes for the 6502. Basically what this is doing is I'm loading a number of 37 so that I can count down to 0. And each time that it counts down, I sync a line. That's a scan line going across. So this is really cool. This is one of the smartest things they did on this machine. This WSync is a strobed register. It doesn't matter what value I put in there. I can put anything in it. And what it will do is basically stop everything until the TV gets to the beginning of the next scan line. So the beauty of this is I know exactly where that thing is. And again, if I lose count for various reasons, like I have some decisions or conditions that changed, and I don't know how long that took me in code to get there, I can just pause, wait for the sync line, and then start up again, right? As long as I'm in a certain range. So all this little loop of code is doing is counting to 37 and syncing, waiting for that sync 37 times. And then when it's done here, when it actually hits 0, this line, and again, I won't go into a lot of detail, but this line says, okay, we're done looping, and we can go on to the next line of code. The next line of code, there's the 192. So from here to here is the picture. That's the game. That's the part we see. I didn't do anything in there yet, but this is where everything's going to go once we actually get to it. And then this little chunk at the bottom is the 30 lines of overscan. And again, we can do a little bit in there. We can't really draw pictures to the screen, but we could perhaps sneak a little bit of logic in here. I'm going to, for fun, go ahead and compile this real quick. And again, I have a pretty clear map to this. If you're playing with the file or you want to play with it later, I have the basic command you would need for DASM for any of the 3 operating systems you might be using. So this is exciting. I like that 0 right there. It means I didn't make any mistakes. Sometimes while I'm yapping on stage, I'll accidentally hit the keyboard and throw some characters in there that the compiler doesn't like. And from there, so I compiled a ROM called VCF1.bin, and I'm going to jump out to Stella here, and that's not Stella. I'm going to jump out to my emulator here, and That should have refreshed. There it is. I am now emulating. You want to learn about this? Why do we do this? And to me, having limitations is the secret to creativity. When you are absolutely limited in an area, you start to think, how can I get what I need done in a tiny amount of space or a tiny amount of time? And those limitations, I think, really created the ingenuity that turned into our game culture right now. So there it is. I got a black screen. I'm going to jump to another piece of code. There it is. Down where the picture's being drawn, so there's this chunk of 192 visible lines. I've added a whole bunch here. The initial thing, the next step that I would have done is just added those 2 lines. So what we're looking here at these 2 lines is actually using one of the drawing registers. And this is a good one to get started on. So I'm loading a value into the accumulator, and then I'm stashing the accumulator into this register that is called color luminance for the background. And so this is going to take whatever color 80 is and write it to the background. And it happens to be a lovely blue. And in this file, and people have mapped. I don't think that's true. I feel like this row and this row are the same. And it hardly matters because some of those colors are close together. What's actually happening here is there's basically 0 through F, 16 different colors, and then there's different luminance ranges of those colors, so how bright they are. That's kind of what's happening. It gets a little murky when you kind of go from one color into another, like these oranges into greens. But that's the idea of it. We're obviously not putting high-resolution pictures on here, so this was enough to get the job done. Initially, when this machine came out, they called it a 4-color machine. They thought there would be 4 colors on the screen at the same time. And when I go back to, I should just leave it open. Why do I keep closing it? When I go back to this guy, you can kind of see where that came from. So you have a register, COLUP0. This is the color of player 0. They called it player 0 and player 1 instead of player 1 and player 2. And so my tank on the left is that color, and my tank on the right is that color, and the scores happen to match for various reasons. If either of those tanks fire a bullet, that bullet happens to also be the same color. We could switch that up a little bit. The background is a color, and so that's the register I just used, that color luminance background register. And then the environment, so if you were going to put anything else on the screen, draw pictures in the background, things like that, that could be another color. And that was it. And that's the way they did it for a while. So this is how you do that. You stash a color in that register, and it's latched. So in fact, you could do it before the game starts, and those colors will maintain throughout the game, which is really nice. So I don't necessarily have to waste cycles doing it. I am doing that here because later on I have intentions of changing those colors. which is one of the early tricks that people figured out about this machine. I won't bother with the compile just that because I'm in a separate file. But the next thing I would want to do after I got some color on the screen would be to actually get a sprite on the screen. So we're going to play around with player 0, and it is tricky. I think this is one of the hardest parts about the Atari. So this chunk of code right here, let me scroll down a little bit. And again, this is within the 192. Let me kind of explain what's happening here. I created a variable at the top, Y position, which is where on the screen that I want the sprite to be once I draw it. And then I also created this name to represent the height of the sprite. Sprites in Atari had to be 1 byte wide, so 8 bits. So they could have 8 pixels. Those pixels could be on or off. When they were on, they were the color you assigned to the register. When they were off, they were the background color. And that's it. But they could be as tall as the whole screen, and there were a couple games that did this. So instead of using it as a character, they could use it as a wall or a force field or something like that. So this is basically starting with my 192. I shouldn't be standing in front of it like this. This is basically starting with my 192, and then which is up here in a line. And then as it's decrementing, it's going through and it's checking, it's looking for the position of the sprite within those 192. I happen to put it at 100 right here. And when it finds it, it says, okay, we're in the sprite. So for all of the scan lines where a sprite is being drawn, that number is going to be passed down to this chunk of code. And if the sprite's not being drawn, we're going to pass this 0 down. We're just going to load a 0 in there and use it. Let me jump to the fun part. Here it is. This is art. Right here. Art on the Atari. So this is my actual sprite. This is how you draw sprites in here. For various reasons, I drew this upside down. When you see decompiles of other people's codes, sometimes they're upside down, sometimes they're right side up. I find this a little easier when people are starting. I know it seems strange that drawing upside down would be easier, but when you're actually counting the scan lines, it is a little easier to understand what's going on. What's happening here is I have this padding byte of 0. The way my code is set up, and again, there's a bunch of different ways to do that, but the way my code is set up here, when the sprite is not being drawn, the command to draw is still there, but I'm putting 0 graphics in. There's no graphics there, so it goes through and it pretends it's going to draw, and then nothing shows up on the screen, which is fine. And so in every case that there is no sprite, it's going to draw this line with 0 pixels on it. From here on out, and if you squint your eyes and step back a little bit, you can kind of see a picture in there, right? So that is an upside down, something that looks like a Space Invader from Space Invaders with 2 little antennas. And I drew some X's over here so you can kind of see it. If the lines were squished together, you'd get a sense of that. And now you see exactly why the graphics could only be 8 pixels wide. So let me hop back up here to where we're actually drawing it. I feel like I'm speeding through it, but we're already a half hour in, aren't we? This chunk of line is basically, I'm moving my accumulator over to the Y variable so that I can use it as an index into the drawing. And this is basically collecting which line on the sprite drawing I'm in. And then I'm waiting for that sync. And then I am writing the graphic to this register. GRP0, that's the graphics for player 0. All of these different graphics that you learn to memorize really quickly are in the Stella manual, that manual written in 1979. And I provided that in the zip if you haven't seen that one before. This next chunk right here, I'm actually going a little crazy, and I thought I would make a color lookup table. So at the same time that each line of pixels, each scan line of the sprite is being drawn, I can change the color. That was not in the intentional design, but I'm not doing anything else with my time right now in code, so I can draw some pretty pictures. So what I did with that one, it actually works the same way. I'm using Y as the same index, and I'm going down here to color frames. And these hex, this could be a little confusing. These hex represent the different colors. And again, yeah, I don't think I'll bother pulling it up. This basically is for the first nibble, the first part of this is the color, and then the second part is the luminance, right? And there's a nice graph inside the manual that tells you exactly what colors you're getting. Being an empirical coder, I was so excited when I first started doing this that I just started stabbing numbers in there to see what colors pop up. And you get some really nice muddy browns, and you get some crazy blues, and you never get the red you want, ever, ever. But there's a lot you can do with it, so it's kind of fun. Let's see. I'll go ahead and compile this one real quick so you guys can see it. I got a lot of windows open and a little bit of space. There it is, not very exciting. All those lines of code. So here's the 2 lines of code that created the blue background. So if you remember, I took the 80 and stuffed it into the register called color luminance background. And then there's my sprite. Now it's drawn right side up because I was starting at the top and working down from the bottom. It's interesting, in other game consoles I've programmed for over the years, there's usually a convention where you have an origin. You know where 0, 0 is on the screen. In the Atari, you put it where you need it at that moment. So I happen to be working from the bottom in this case because it's a little easier to count time. And you can kind of see the variation in colors that I threw in there. So you can see each scan line is different. Note that this and this wouldn't actually be on a real TV screen if I was looking at this on an NTSC screen. So that color register in this particular emulator blows over the blanks, which I question in a real TV, but I seem to have some deep repressed memory of there being color going all the way to the edge of the TV on a real tube television. That was a lot, and we didn't even start. Instead of talking about code, well, I'll talk about the code a little bit, but instead of going deeper into code, I'll lighten up a little bit and talk about things more generally. This is step 1 if you're learning to create games for the Atari, just getting something on the screen. And frankly, it doesn't matter what you're programming on. This is our version of a hello world. First, I always try to get 1 pixel on the screen. Once I get a pixel on the screen, I want a sprite on the screen. My next step is to move it. Well, there's a little trick here. I kind of evaded something as I was going through all this code. We know that this is at scan line 100 out of 192, but I didn't tell you how I got it in the middle of the screen. And in fact, it's almost a little bit of a mystery. So there is this nice line that they provided. I'm going to move around a little code to show you guys how this works. I'm going to take my sync here. This is actually just writing to registers, so the sync doesn't have to be exactly at this spot. And luckily, my code, so each line of code that I'm using, I can look up and see how many cycles that is. For instance, if I'm loading the accumulator, I know that that's 2 cycles, machine cycles. Those cycles equate out to color cycles on the television interface adapter, that other chip. And for each cycle, that one expects 3. So now I know that I can draw in chunks of 3, or I can time things in chunks of 3 going across the screen, which is not great resolution when I'm already a low resolution. And if I used that system and had something move to the left or right across the screen, we'd actually see it hopping as it goes. So Atari was lazy enough, no, lazy is not the right word. They were brilliant enough to let the programmers deal with that problem. But they realized that this would make some ugly games, so they actually did create a register to get a little more finesse in there. So there is a fine register to move left and right just a little bit, just fractions, so it can go back and forth from where you could get it timed in code. Very kind. I'm going to move this guy down so you can get a sense of how this works. I don't know why I brought my Windows machine. That was silly. Let's see. I'll do it right here. So after I write to the register. I have seen 100 comment-long arguments on the internet about why this is not all the way to the left. And there's a lot going on there, and frankly, I'm not completely positive of the reason, but I know that I can use that fine register to slide it over a little farther if I have to. But to get it across the screen in major steps, I now have to fill this loop of code. The distance or the timing between my two lines, 60 and 61, the amount of cycles that are wasted in there, the more that are wasted, the farther to the right it'll move, right? So if I put in there, let's say I increment a register, that'll take 2 cycles. If I have a branch in there, where maybe I'm trying to go crazy and make a decision during one scan line on a television, that'll take 3. And in general, if you add those together, you can get 5 as kind of the tiniest little increment that we can figure out how to do this efficiently. So we have steps of 5 that we can go across the screen. And again, not enough. That's going to be a really jittery picture as I go across. But I can use that fine register to move it a little bit to the left or a little bit to the right. If I know how I'm doing it, I can preset the register before the scan line starts. So I'm saving a couple cycles of code in there. That's it. That's the heart of it. So now I know how to move something left and right. Reading the joystick after this nightmare, if you can wrap your brain around this, reading the joystick is actually fun. You literally just read a register, figure out if it's a 1 or 0, and apply it to whatever variable or change that you wanted to happen within your game. This guy again, right? Now we run into something interesting. Anybody who's played this game, first we have a multicolor sprite. So I know how they're doing that, right? I just did it, and that's sucking up a lot of cycles. Plus it moves really smoothly across the screen. So I know that they're using almost every bit of code to the left of the character within that scan line. It's being sucked up by code, and in this case, I'm guessing this programmer really needed that code to do logic and operations. And then there's places where you're drawing 2 sprites on the same line. Depending on which 2, that's easy. If it's another 2, it means you have to repeat that whole cycle, and it'll take the same amount of time, and so you have to interlace that in the code and pay attention to how you're doing that. And then on top of it, you've got this background, right? And that has to be drawn in that amount of time. So I know that some amount of cycles is being used up for that. And then I have no idea, to be honest, how they're doing this in this piece of code. And I should probably spend a lot of time with the decompile. I haven't seen good remarks on this file yet, which I still need, frankly. to be able to read code and really understand the logic behind it. But remember there's player 0, I'm guessing is here. Maybe player 1, because I know this is moving in the screen. Occasionally I've seen 2 or 3 skulls rolling across the screen in this game. And what I'm guessing is happening with that is they're actually not drawing every frame. So they are storing a variable and counting frames and saying, okay, I'm going to draw this every 3rd frame, or maybe even every 5th frame. And anybody who's played Atari games knows on the more exciting games, things start looking really flickery. To the point right around the video game crash when the port of Pac-Man comes out on this thing, and you could barely see the ghosts if they were near each other, right? Because they were only showing up maybe every 20 frames. We only have 30. We only have 30 to work with, right? So 2/3 of the time, they're not on the screen. I know that these, if we weren't in a still, I know that these are force fields, and they're kind of blinky and shaky. That's kind of interesting. I feel like the programmer might have known that this was going to be the case because they're splitting this over multiple frames, and so they're using it as part of the story. They're using that aspect of it, this kind of blinky, faded look to it, and say, oh, yeah, I meant to do that, right? And just being very careful about which sprites they're picking to do that. That was a lot. I don't know where we are in time. I think I got to most of the end of this. Again, if you're playing with this file, I've been teaching this stuff for years, but I based a lot of this on something called 8-Bit Workshop, which is online, and an excellent book designed by Steve Hugg. Is he here? I always wonder when I'm talking about people on stage. No? He's probably online, like, you pronounced my name wrong. I highly recommend it. If you are really interested in this, this is a great way for people who are coming from almost no programming to get into this. It has very, very nice step-by-step, much slower than what I'm going through here. If 6502 is a whole nother world, and you might want to try your hand at that first and just get to do some math and things in 6502. And I imagine that there are more resources in Camp Evans right now for 6502 than the whole rest of the country. So ask around and look around while you're talking to people. Questions? Well, that was easy. I said an awful lot. I think I showed nothing. It's that thing again. The more constraints you have to work with, the more creativity. And Atari gives us practically nothing, which makes me feel like we can be pretty creative with it.
Explain this, what you just said about the resources that were available back then and this and the 2K that you had to work with to somebody younger that's been programming and stuff like that. What are they?
Yeah, what does that mean? Yeah.
How can you tell somebody that you had to work within a 2K space and now they have gigs and gigs
Yeah.
and this stuff was made
in that amount of space. Yeah, it's tough. And again, over years of teaching, once upon a time I used to say in my classroom, does anybody have a cell phone? Right, because I could start talking about the memory on the cell phone, because when not this kind, right, the little flippy ones, when they came out, they had about the same memory on here, right? And people, boy, if they were lucky, they had Snake on their phone that they could play, right? I teach in something called Unity now, which is a game engine that is absolutely insane. And there's this whole culture in game design that's been happening for a while, and it's kind of evening out, where people are really wasteful of the computer resources because we can be, right? So, overmodel, overpack. Don't worry about trimming your sprites. Trim them in code, or let some whole library that you loaded up do that trimming for you. Yeah, it's kind of hard to explain. I actually teach this as part of my history class. So I'm a weird professor. I don't like to give tests. So when I teach video game history, instead of giving tests, I say, okay, we're going to make a program. We're going to make a game. And they get it really quick. Again, I've not had a lot of luck moving this particular one into the classroom. I love it. I think if I had upper-level comp sci students, they'd be okay with it. But Chip 8 is a great gateway drug as far as assembly language coding goes. And you need to be really efficient. They especially understand it when they start creating graphics like that, you know? And I'll Photoshop, and this kind of hammers it home. Open Photoshop and open a file. Photoshop can do millions of pixels, right? Open a file that is 8 by 8 pixels. And then we're going to draw one of these, right? And I have them use the pencil tool, and I have them clear out the dithering, so you're either drawing or you're not, 1 or 0, right? And the funniest thing about it is when I have them do it, yeah, no problem. I know how to open a file. I know how to change the file size. And then they zoom and zoom and zoom and zoom and zoom. And then they get to the farthest range that the computer can handle, and it's still this big on their screen, right? And at that moment, they're like, oh, that's what 8 by 8 pixels is, right? Compared to, you know, they've been playing Fall Guys or whatever game came out last week. Other questions? Yeah.
I've done Atari program. I've never done Chip 8. What would you say is like the difference for someone entering it for the first time, like between those two?
Yeah. So Chip 8, and the reason that I teach Chip 8 in the classroom, it has a screen buffer. So I can actually draw everything on the screen, and it won't tear. I don't have to worry about timing. If I accidentally put it in the wrong place, it's visually in the wrong place, I'll move it. So it's very nice to do empirically. Atari, and again, I mentioned as a visual artist, I'm an empirical programmer. I try it, see if it works, adjust it a little bit, see if it works. I push this to my students. I'm like, you change one line of code, recompile and look at it, because you may have destroyed it, right? It's very hard to do this in here because it's so much work just to get the initial image on the screen. And then slight things like just moving a sprite, if you are not slick with your code, you can move it into the next scan line, which pushes the next scan line, which pushes the next scan line, and all of a sudden you have this crazy moving overlay happening on the screen. Chip 8 is also not color. There is a color version of Chip 8 that came out a couple years later. I don't mess with that. I love Chip 8 because it ran on old machines, you know, the RCA Cosmac, the RCA Studio 2, that old video game that no one ever talks about. And it works. And it's a portable language, and I think the students appreciate that. Yeah, we can do anything in emulators. Calculators, they could squeeze games onto it. And Chip 8 was one of the first languages that got onto those calculators. So it's a fun one, but frankly, the screen buffer, that's what changed everything in all the consoles that came after this. Are we good? Other questions? I'm gonna be around all day if you catch me in the street. I'm happy to chat all day. All right, thanks for your time.
Hello? Hello. This one works.
Okay. All right, give me a
That's why
moment
we
to get
got
clipped.
That
Okay,
one's really
all right. Bear with us here while we get this dealt with. Oh, holy care. Can everybody hear me okay? All right. Good morning, everyone. Okay, this particular class right here is for programming the Fujinet. For those that don't know, the Fujinet is an 8-bit network adapter for Atari 8-bit machines. It will be coming to other machines shortly. You can start to get information by going to fujinet.online, which will give you a good overview of what the network adapter can do in terms of its capabilities. But just as a quick overview, it provides a virtual disk interface, allowing you to load disk images over the network or through local storage. It provides a Wi-Fi modem. It provides a virtual printer, emulating a wide variety of printers. And perhaps most interestingly, it provides a full-blown network adapter that does protocol offloading of a wide variety of protocols. And that's what essentially I'm going to be talking about today, is showing you how you can take and create network applications using the programming language of your choice. And in this case, I'm going to be using Atari Basic for that. There's lots of wonderful bits of information that you can get to from the Fujinet.online website. One of the most important resources, especially when you're doing programming for the Fujinet, is to go to the support section and go to the GitHub Wiki. And the GitHub Wiki contains a wealth of information, not just in terms of contributed user documentation on how to use your Fujinet, but also all the programming information that you need, such as the commands that are supported for doing various network functions on Fujinet, both from CIO and SIO. For the purposes of demonstration, we're actually going to be using a wonderful page here called the Basic Networking Cheat Sheet, which shows you, among other things, how to take an open client connections, opening listening sockets, listening for connections, as well as sending, receiving data, and closing the connection. And for the game that we're doing here, we can actually show, I'm actually going to be doing the reversey example here, showing you how we take an existing game adapted in Atari Basic and give it networking capabilities so that two people can play a game of reversey over the network. To start, we need an Atari. Well, good thing here, I have a copy of Altera here, and I also have a copy of Fujinet PC, which also means that not only can you use a real Fujinet device, but you can run the Fujinet software on your PC and connect it to your emulator to take and do software development here using the debugging facilities that are available in the emulator, making development very nice. To start off with, it's actually very simple. We can go ahead, I will completely cold start everything here so that we go back to the Fujinet configuration menu here. And it's going to try to boot DOS. Pardon me while I take and reset the Fujinet just for a moment. And for those who haven't seen it, this is the configuration program that loads when you first turn on your Fujinet. It allows you to connect to both local and remote resources and to mount disk images to set everything up for your environment here. For what we're going to do, I'm actually going to take and use a disk image in the cloud on a host called atariapps.errata.online, which contains a wealth of pre-existing disk images for all sorts of uses. One of the best folders in here is the DOS folder, which contains a wide variety of DOSes, but most importantly, it contains all of the Fujinet utilities and the device driver that you need to use the network functions from other languages or other programs. For the sake of expediency, I'm going to choose OSS DOS XL, but you can do this from any DOS that you wish. I'm going to mount it here, and I'm going to go ahead and I'm going to create a new disk image on my local storage, or actually, sorry, on my local TNFS file server here, and call it Reversi. This will be a fairly standard 90 kilobyte diskette, single density. Say, yes, are you sure? Absolutely, and we're going to mount the result in drive 2. This is a blank disk, so we will have to format it. We'll do that next when we take and boot the system. Go ahead and press F4 to mount everything, if it will let me. Come on. There we go. And within a few moments, it will take and load DOS XL. And since the end device driver is loaded as auto-run sys, it will automatically load the end device handler for us and get it ready for use. And since this is a Fujinet startup disk, it also has the various Fujinet config utilities here that you can use at your disposal. One of them is fconfig, which will show you the current network configuration. We'll go ahead and we'll run init here to format a disk. We'll format a disk and write DOS sys since we have the blank in drive 2. We go ahead and write it there. And it's already written the DOS for us. We go ahead and exit, and we copy a few things over there to help us out. One of those things, of course, is autorun sys, which contains our end device driver, because we're going to need it when we take and boot into this. And we're going to copy a program called do.com, which allows us to do complex batch operations. Particularly, we're going to use it here to load our finished game automatically from the disk when everything starts up. And for the sake of just convenience, I'm going to go ahead and copy the copy command over there as well. Since copy is an extrinsic command in DOS XL, I need a copy of it over here as well. We still have plenty of space on the disk. Now, if we look at what we have DOS sys, we have the end device handler as autorun sys, which will load automatically when the disk is started, and the two utilities which will help us take and build out the last bits and pieces of what we need for this when we finish. So with that, I can go ahead, I can put my DOS XL disk away, which we can do that when we take and recold start the system. I'll use the freset command to do this. And we'll go ahead and eject this and put Reversi into drive 1 here. This is my local TNFS file server. I'll take and put this in, read write into drive 1. And we're just about ready to go. Now, one thing I will do here, since I'm running an Altera, and since Altera can speed up cassette access, which we really want to do in a 30-minute presentation, I will go ahead and load the game that we're going to convert from cassette. This is Roman Checkers. It was sold by Sears as one of the very first games available for the Atari 400-800 machines back in 1979. Okay, and with that, we'll go ahead and before we start actually adapting the game though, I want to show you guys how easy it is to do network communication. To start, we're going to have a window open here. This is a terminal window on my local PC, and I'm going to be running a copy of Netcat, whose whole purpose is to take and listen for connections, accept those connections, and to echo anything that I send to it to this window. It's here listening on port 6502 on all interfaces. And all I have to do to take and establish a network connection is to use the open command that most of us basic programmers know and love in the first place. We're going to use the in device, which has been loaded by autorun.sys. In has a special format that it uses for its device specification, which allows you to specify the protocol that you're wanting to use, in this case TCP, the host name that you're going to connect to, in this case TMA2, separated by a colon, followed by the port number that you wish to listen to, ending with a slash. You'll see immediately that it went ahead and opened up a connection. Now, the one part that you may not be too familiar with is the second value right here. On the wiki, it just explains what this second value is used for. And in this case, we're telling Fujinet to translate carriage returns and line feeds automatically for us so that we don't have to do this in our code. And it will make it easier to communicate with this window over here. Oop, come on, quit it. Okay. All we have to do to send something over the connection, print it. And all we have to do to send something back is to input it. That's it. That is as simple as it gets. If you want to get single bytes, yes?
Isn't this really done with mirrors?
I tried to put as many smoke and mirrors in this as I possibly could. Okay, so that's it. You can use get and put to do individual bytes as well. And the field processing that's available in the input statement, doing comma-separated information, is also possible. So you can input data into multiple variables at the same time. And we're actually going to be using that in Reversi here. So with that, let's go ahead and start adapting our game. We'll go ahead and close the connection here, which will also close the Netcat connection over here. We're done with this for now. Okay, great. Now at this point, since I have a cassette loaded, I'm going to go ahead and just do a C load here. I'm going to let it do its thing, and you can see we do the little thing here. Since we have cassette acceleration turned on, it's pretty much instant, thank God. Because otherwise this would be very painful to wait. And we have our game here. Our game isn't that big to begin with. And in fact, if you want to take and have a nice little listing of this that you can reference, you can send this to the virtual printer, and in a few moments, we can go pick it up in the web interface. Since I'm running Fujinet PC, this is running on my local host on port 8000. Are we done? Yes, we are. Okay. And since I'm using the HTML Atascii printer, I can take and download the finished printout with the Atari font and any special characters that may have shown up here. Very useful for printing out programming listings and the like. Thank you, Jeff, for working on the virtual printer. It's amazing. So, you can see this program isn't that big to begin with. That also means that what we have to do to adapt it for network use isn't that big either. But to start, we'll just go ahead and run it real quick. We have type name, press return, Tom and Bob. It draws the display. It puts up the play field. Now, the first thing that you should always put in mind when you're trying to adapt something for network display, for network use, you need to think about in terms of the types of information that you need to be able to send across. Well, we know that we need to send, first of all, our player names, one to the other, and we know that we need to send our position information, such as when we're selecting a square, when we've selected a square. At the end of the day, that's really all we need to send for this game. Plus, I want to take and make a couple of small changes to the color scheme, because this is terrible. So we'll go ahead and break out of that. If I can. Come on. And yes, the N handler is resilient to resets, so it will stay in memory if you hit the reset button. So to start, we'll make a few adjustments here to the color palette, which is on lines 710 to 720. And for the case of expediency, I'm going to use the magic of cut and paste to do this. So we're going to take those colors right there, and we're going to put something a bit more palatable. Pardon the pun. Okay. Now, if we look at line 500, we'll see that these are all of the variables used in the game. We have A and B for player names. We have the current state of player, and we have board positions, essentially. Not much else. So all we need to do to that, we need to add an additional variable, essentially, for holding the host name, but we also need to add one to hold the device spec that we're going to construct from the host name. And we're going to add one more variable called ls, which is a flag indicating whether we're listening for a connection or if we have connected to another host. At that point, that gives us everything we need to kind of start up. We go ahead, open up the keyboard here, start up, type name, press return. Now this is where we start adding in the meat of what we're going to add for our game here. We're going to take and add a little message to the screen saying be sure to forward ports and ask for a host name as well as return to listen. Now, I'm going to use a particular trick here called input number 16. And this particular trick basically suppresses the question mark in an input statement. So if you've ever wanted to do that in Atari Basic, this is literally how you do it. We're going to take and see if the host name is blank, that is, you pressed enter, and if it is, we assume that we want to listen for a connection. And finally, we go ahead and we construct a device specification. Oops, my apologies. Using the string functions in Atari Basic to basically take the host name that we've input and put a device spec around it with the appropriate port. We then immediately open that device specification. Now, for the purposes of testing, I'm going to change the 0 to a 2, again, so I can use this with my netcat window. Since netcat is running in Unix, and Unix uses line by themselves for carriage returns, the 2 means just only deal with the line feed and not try to add an additional carriage return. If we're not listening, then we take and jump over this next part where we try to listen for the connection. Otherwise, we continuously put ourselves in a loop where we get the status of the connection that we just opened and see, based on status, if you've ever worked with status before, canonically, status puts its information in location 746 to 749. 748 in this case is where the end device driver puts its connected or not connected flag. So you can tell whether or not you've connected or not by seeing if you jump out of this loop. If we jump out of this loop at any given time, then we have a connection waiting for us to accept. And you'll notice I'm using a particular convention here called ASCA, and that's because otherwise this would be the number 65, which is the ASCII value for capital A. At least doing it this way, it becomes clear that we're essentially using capital letter A here to indicate that we're accepting a connection. At this point, if there's a connection waiting, it will take and bind it to the I/O channel of our choice, which in this case is number 2, and then continue on. At that point, the Atari has accepted the connection, and you can read and write to it. We then wait for a moment for that to finish. And I think, give me just a moment to take and turn off input for joystick here for just a split second. Well, there we go. And now we get down into 600 and 700. This whole section right here, we're basically going to be jumping over, because we really don't need all of it anymore, because some of this is being taken care of by the network now. So we start by saying, if we're not listening, let's go to line 620, where we ask for player 2's name. Otherwise, we take and get the player name from the network port, send ours, we send our network name, we get the other player's name, and then we immediately jump to start the game, which is on line 700. Conversely, if we are listening, then we do the opposite. Finally, we get to the meat of the game itself. And this is pretty much it in a nutshell. And we can zoom in a bit further to here, and you can see this is where we spend the majority of the time dealing with joystick or keyboard input and deciding what to do with that based on what we get from either the joystick or the keyboard. We'll go ahead and modify line 1510 ever so slightly mostly because we're only dealing with one potential joystick or keyboard input, so we can simplify this just a little bit. Oops. Apologies. Do that again. And finally, we figure out if we're listening or not, and then we figure out if we need to take and jump back to the beginning of the loop. Finally, we modify 1530 ever so slightly to deal with the fact that we're now getting information out of the network. Now, to take and send our player information, this is all we have to do. You can see right here that we are constructing a string that sends the X and Y information separated by commas. And that will make it very easy to take and read the resulting inputs when we're done. We need to, for various different reasons, we need to do it not only when we move the cursor, but we also need to do it when the trigger is also depressed. And finally, if we look at the top of the program, you have various subroutines for different things that we need. In our case, we actually need to add an additional bit of code to after line 60 here, which is every time that the move changes and there's a delay here, but we also need to check to see if there's any input waiting using the status command, and if there is, peak 746 will tell you how many bytes are waiting, and if it is, we go ahead, and because we've comma formatted everything ahead of time, we can simply take and input all of our variables at the same time. And if trigger is set, that means the trigger is pressed and we want to do the move, we go ahead and jump to the part of the code which takes and inputs the move to the game engine itself. That's it. Using a handful of lines of code here, using input and print statements, we've basically added network functionality to an existing game. And that took, what, 10 minutes? If we go ahead and start it, and I'm going to go ahead and I'm going to do the same thing I did before with this window here, and we're going to use netcat as our test so you can see what's happening across the network when we play this. Using the same port as before, netcat, listening, and we'll connect. Connection received, and we immediately put our player name here. Apologies. And I'll go ahead and put Bob. And the moment we do that, it's going to send that across the line here for us. And I'm going to take and respond with my player name over here. Now we'll see, we also see the new color changes as well. Now, I'm going to go ahead and turn on my joystick to arrows. Are you going to let me do this? No? Oh, wait, probably because I need to take and do it over here. And you'll see, as I take and send network commands over, it's actually taking and updating the position over here. Go ahead and do this again. Let's see. There we go. I'll select that piece. Is it going to be legal? No, it's not. I'm just kind of improvising here. But you can see how we can take and bounce back and forth. So we'll go ahead and stop this here. And I'm going to take and load this on another virtual Atari here. And we'll see if we can do a game. I'm really testing fate here. So for that, I'm going to go ahead and open up a virtual machine, which I have suspended. Come on. Come on, what are you doing? Are you not going to let me do this? Okay, we might be stuck here. I guess I can take and end it here, and if anybody has any questions, go ahead and ask.
What set you down this road?
You got another 2 hours? Well, basically, I wanted to create, Moswald and I wanted to create an 8-bit network adapter that was easy enough to use. And one of the use cases that we had when we were thinking about how we were going to program this thing, we knew we didn't want it to be like existing 8-bit network adapters like the Dragon Cart, Ethernet, et cetera, because those devices are notoriously difficult to program. We wanted something that if you wanted to submit something for the 10-liner basic contest, you could. And we wanted to maximize the ability to integrate into the operating system as best as we possibly could.
Tom, didn't it start as like an adapter put into the Fedotherm box? Isn't that how it started?
That was one of the things that we wanted to do. I wanted to make good on a connectivity solution so that people could connect to Errata Online and services like it. And it just so happened that while we were going down that line, Moswald had created this ESP8266-like device. And more importantly, he had hooked up all the lines. And it all started with the basic question, is the command line hooked up? Well, if the command line is hooked up, that means I can simulate any device that we want to. And, well, proceed and interrupt is hooked up as well. So we were able to make network communication efficient. And it sort of went from there. The thought process became, how could we make something that integrated well into the Atari operating system and be able to utilize all of its various functions?
And then with all those lines hooked up, Moswell turned it into a MIDI device to do MIDI maze.
And that's another part of it too. We're hoping to be able to take and generalize that so that other games that need constant stream-based input and output without disrupting the system, waiting for packets to come in, will be able to utilize that as well. Anything else?
What other systems do you have in the shoot next?
Well, we have Commodore 64 has been breathing now for a couple of months. Well, we have a couple of Atoms here, Coleco Atoms here, that I'm going to be doing the first bits of system bring up here once I finish here. I'm spending the rest of the day basically seeing if we can take the prototype boards that Moswald has express shipped over here to see if we can do the first network boot up with it. Apple II via the Smart Port, and if we can work out a bus interface, potentially other systems as well, not just computers, but game consoles. The beautiful thing about the ESP32, I only went over TCP communication in this particular round. But there are many protocols that the end device can actually deal with. HTTP, HTTPS, encrypted protocols such as SSH, SSL, etc. And the ESP32, since it's a much larger, much beefier machine, can handle all of the intricacies of talking that protocol, handling the encryption, and doing everything that it needs to do so that the Atari gets a nice, clean I/O interface.
And Tom, what other languages, 8-bit languages, do you have examples in?
We have, if you actually, one of the nice examples that you have, if we actually go to the wiki page, you can see, for example, programming information, and we have a simple netcat program, which does exactly what you saw in my terminal window here, providing a basic terminal-like program. And we have examples of that in BASIC. As you can see right here, it's like 6 lines of code in BASIC. There's a version in C, using C65. There's a version entirely in assembler, for those who want to do this in assembler. And there's also, I did another example and another series of videos showing how to do that same program in action. But basically, any language that you want to use on the Atari, you can. I've even done this from Logo. Pilot should work, but it does something very, very nasty to the device handler table that I haven't been able to figure out what's happening yet. But it would have worked from Pilot as well. Basically, anything that supports central input and output will work. And if you don't want to use central input and output, you can talk directly over SIO.
Less technical, but what's the inspiration for the name?
You can thank Kay Savitz for that name. Originally, this project was called Atari Wi-Fi, but we changed that because said company tends to be rather lawsuit happy. So we decided we needed a quick name, and Kay kind of threw it out there and went, oh, that works. And, you know, Atari, Fuji, you know, logo worked out perfect. So. Plus, it's just generic enough that people who aren't as familiar with Atari can basically aren't going to immediately go, ooh, it's Atari thing, I'm not going to touch it. So. Any other questions? Okay, thank you very much.
How do people get one, Tom?
That's the beautiful thing. Fujinet is an open source project. Open source in terms of software and in terms of hardware. This means that we have multiple vendors that are building these. You can get a Fujinet either from fujinet.online when Moswald builds limited runs. You can get them from the Vintage Computer Center, VCC, and you can get them from the Brewing Academy as well. In Europe, you can get them from Zaxxon and retrolemon.uk. Anybody who wants to take and be a vendor, we can work with them to bootstrap them to show them how to make it. Because we want this thing to be used everywhere.
Do you have any idea how many of them sold?
Yeah, actually, close to 2,000 since the version 1.0 late last year. I know, I'm surprised too. Okay. Thank you very much.
I'm Stephen Edwards, and I'm going to talk about the personal computer graphics of the 1960s and 70s. I'm going to start by teaching you about the cathode ray tube, or CRT, that forms the basis. Action voltages that control where the spot goes on the screen, and then the control grid, which controls the brightness. If you want a stable image to appear, you need to be constantly redrawing the same image 60 times a second. Here's the DEC Program Data Processor, or PDP-1, circa 1960. This wasn't the first, but certainly an early important computer that had a CRT display. This particular machine is equipped with a Type 30 CRT display, one of the original peripherals offered with the PDP-1. They marketed it at the time for displaying scientific data, graphs, things like that. But of course, we really know the main purpose of this was to play Space War. Space War is a two-player game in which each player controls a spaceship. There's a star field. It simulates the effect of gravity from the sun at the center. The spaceships will orbit around the sun given the opportunity, or they'll just shoot each other. Note the tails that the starships have. This is due to the long persistence of the phosphor in the monitor used in the Type 30. The Type 30 consists of a CRT mounted in a very science fiction looking cabinet atop a desk. The desk itself was actually filled with the electronics, in particular a bunch of power supplies, plus the analog and digital circuitry needed to make it all work. Here's a block diagram. Broadly, it consists of two 10-bit digital analog converters, one for horizontal and one for vertical. 10 bits is pretty remarkable. This means that these monitors had a resolution of 1024 by 1024. It also had the ability to control the intensity, the brightness of the spot being drawn at any moment. To display an image like Space War, the PDP-1 would have to be constantly feeding new coordinates to the horizontal and vertical buffers here, shown at the bottom. These would then change the deflection to point the electron beam at different places on the CRT. It would have to be constantly doing this to give a stable image. By the standards of the time, the PDP-1 was about as personal a computer as you could find, but that doesn't mean it was cheap. Here's a price list from February of 1963. The base PDP-1, with a whopping 4K words of memory, would set you back $120,000. The CRT, with this controller, would set you back another $14,000. And if you really wanted to be luxurious and spring for a symbol generator that would let you display characters more easily on the screen, that would be another nearly $5,000. The way the symbol generator worked was an additional add-on card or set of cards that you would put in the Type 30 that would let it display a 5x7 matrix. Now, this was totally BYOF, that is, bring your own font. The processor itself would have to feed the 5x7 matrix for each character to the symbol generator. It didn't have a built-in font. 4 years later, in 1964, Control Data released the 6600, which is sometimes referred to as the world's first supercomputer. This was actually designed by Seymour Cray of Cray Computer fame while he was still at Control Data. Even more expensive than the PDP-1, maybe $2 million at the time, something like that. This was an amazing machine. A very RISC-like 60-bit central processor ran at 10 megahertz. And the reason we're talking about it here is that it had a rather menacing-looking dual vector monitor display for the console. Like the PDP-1's vector display, it still needed refresh. What was very novel about the 6600 is that in addition to the very, very fast central processor, it had a series of I/O processors designed to manage things like disks and tape and a display. These were much less powerful things. There was actually only one of them that was essentially time multiplexed, but the result was that these I/O processors could handle the vector display refresh automatically. These functioned in many ways as DMA controllers as well, in that they were able to get at the rather sizable central memory for the time. Amusingly, the way this would work is that you'd have the 6600, you would connect up a 6602 console display controller. This was another rack of electronics. And you could connect it up to two consoles for a total of 4 vector CRTs. And the way this worked was the console display controller only had one channel for all of its data, but could send the horizontal and vertical deflection stuff to all 4 vector CRTs and then turn on the beam for just one of the displays. The other 3 would be turned off. Unlike the PDP-11, this used 9-bit digital to analog converters, so only 512 by 512 resolution. The CRTs themselves were a little bit smaller, 212-inch instead of a 19-inch. Interestingly, this always had character displays built in. Unlike the PDP-11, they were vector character displays, and in it they had manually coded in something that's a little bit like a ROM, but was actually closer to discrete logic, vector versions of each character that would then be displayed. The way this would work was they actually had analog amplifiers that would add a base coordinate, this is where the lower left corner of the character would be displayed, and a small offset depending on where you were in the character itself. Furthermore, you could change the gain on the amplifier that added these two such that you could get larger or smaller characters, which was kind of a neat idea. Realistically, though, vector displays like this and the one on the PDP-11 ended up being a dead end. They were quite high resolution, amazingly, 512 or 1,000 pixels across, amazing for the 1960s, and would require relatively little memory. For something like Space War, really the program was worrying about how to generate the location of the ships and so forth. There wasn't a lot of memory required for that. The problem is that you couldn't really fill regions. The best you could do is sort of text and wireframe images, and flicker was constantly a problem. The refresh rate would vary depending on how complicated the scene was that you were trying to display, and would flicker like crazy. This was still an interesting technology. Atari used it in commercial vector arcade games in the 70s and into the 80s. And there was even a consumer vector video game console. This was released in 1982 called the Vectrex, which is popular among collectors at the moment. But again, this was a dead end. Raster displays had been known for a long time, and in fact was the original way that video has always been done. Unlike vector displays, they always start at the top left, draw to the right, then go down a line, start again on the left, go to the right, so forth and so on, scanning repeatedly. The problem with raster displays, even more so than vector displays, is you have to keep them fed. Not only do you have to draw everything that you want on the screen, you have to keep feeding the data even in the dark areas and know that they're dark. This takes more effort than just doing a vector display. So-called glass teletypes, because they were character terminals designed to emulate the printing terminals of the time, were growing in importance in the early 60s. Here's one from 1964. This is IBM's 2260 that could display 6 or 12 rows of 40 or 80 characters, depending on how much money you wanted to spend. It could display 64 different characters on the screen, so if you wanted lowercase, you were out of luck. It could do a raster display, but was unusual in that it did a vertical raster. So instead of scanning rows, it scanned columns. Why IBM chose to do this is not clear. The 2260 itself, the terminal that we think of, consists of a keyboard and essentially a composite video monitor. Now, this being 1964, the monitor itself, in addition to the CRT, used vacuum tubes internally for many of the amplifiers. There were a handful of semiconductors, but pretty rare. Even more interesting was how they stored the contents of the screen. Say you had a 12 by 40 display. You needed to remember 480 characters, each 6 bits wide. The way IBM did it is with a sonic delay line. Core memory, which was the standard way to store data, was much too expensive for a terminal like this. So this is the solution they came up with. Internally, this sonic delay line consists of a long coiled piece of wire with transducers at the front and end. What would happen is one of the transducers would make sound. It would travel through the speed of sound in the wire down to the other end, and then be retrieved at the other end. To use this effectively as a memory, the output would have to immediately be recirculated to the input. But this is exactly what you want to be displaying a video image. You need to keep refreshing it, so you keep revisiting the same data again and again and again to describe it. Even more amusingly about the 2260, it used core, but for storing the character ROMs. So it actually had 64 individual core matrices, one for each of the displayable characters, and the 6 bits selecting the character would select which of those cores to read from, and then drag that information out, serialize it, and send it to the video monitor. Amusingly, since these cores were not meant to be changed, rather than populating every location with a ferrite core, they only populated the ones. So Here's a diagram showing how they used the core matrix and only filled in certain locations in it with ferrite cores to get the character that they wanted. Here is a capital A. By 1970, semiconductors had advanced to the point where semiconductor memory could be used for effective character terminals. This is what DEC did with its first serial character terminal, the VT05, which was quickly replaced by other things that are better known, but this is still important in that it was the first. The display on the VT05 consisted of 20 lines of 72 capital letters each. You can see it here, for a total of 1440 characters. Unlike the IBM and CDC displays, integrated circuits allowed the VT05 to have all of its circuitry in one relatively large box by today's standards, but in particular there was no 19-inch rack behind it. Here's the interesting part of the block diagram of the VT05. From the left, we have the frame refresh memory. So this stores the characters, and here they're actually listing out 9,216 bits total of frame refresh memory. Following that, we have the line refresh memory. This is more modest at 600 bits. And the idea is that this held enough characters for a single line and would recirculate around multiple lines until the next row of characters needed to be displayed and brought in from frame refresh memory. Then it took the 6 bits representing each character and put them into a ROM character generator that would spit out 5 bits that would then be serialized and turned into the video signal itself. Here's the schematic for the frame memory. Gone is the bizarre sonic delay line of the IBM terminal we looked at, and in its place are 9 Intel 1402 shift registers. Each of these chips has 4 256-bit shift registers in them, and as you can see, they're chained into 6 columns each, giving us a shift register of 1,536 bits wide. There are then 6 rows of these, and that's where we get our 9,216 bits total. Was advertised as containing 1024 bits, that is 4 banks of 256 each, could operate at 5 megahertz, and was dynamic in the sense that it would lose its memory if it did not keep circulating. But in the application of a character display, you have to constantly be circulating the data anyway, so that it was dynamic was no problem at all. Here's a die photo of a similar chip, the 1405, of a similar vintage, and you can see how it was laid out. It's just row after row, and what happens is bits move right down the row, then they move left down the next row, right down the next row, so forth and so on. Here's the schematic for the line and character circuitry. The line memory was built out of 3 Intel 1507 shift registers, each of which consist of 2 100-bit shift registers internally. So 3 of these gave us the 6 bits that we needed. This also gives us the 600 bits total that it was bragging about. These are fed from the line memory, but can also recirculate, and you can see the logic for doing that here. The 6 bits from the line memory are fed into a national MM5240 character generator ROM. This has the uppercase character set in it to be able to display, again, 64 different characters. It would spit out 5 bits per row, and then you could select which row of the character that you'd like. By 1973, the cost of the integrated circuits needed to do a delay line-based character display had dropped to the point where it fell into the realm of what hobbyists could do. Don Lancaster published in Radio Electronics in 1973 a groundbreaking article on the TV typewriter. This was a design really fairly similar to the VT05, but within a hobbyist price range. It consisted of a bunch of boards, a keyboard of some sort, and the ability to spit out video that you could then send into a TV, hence the name. Here's the schematic. Its structure at its core is very similar to the VTO5. We have 6 Signetics 2425 512-bit dynamic shift registers. This is storing the screen memory. There's a 2518 6-bit wide line register that stores the characters for a single line. There's the Signetics 2513 character generator, and that feeds into a parallel to serial chip, the 64165 here. The 2513 is a 64 by 8 by 5 ROM that has in it a fairly familiar looking font. And I'll give you a hint about where you might have seen that font before. Here's a schematic with a very similar setup. We have a 2513 character ROM feeding into a 74166 parallel to serial converter. We have a 2519 very similar line buffer chip. And then we have a collection of 2504 shift register chips used to hold the entire display. Now, if you don't recognize this schematic, and you really should, let me zoom out a little bit. You may have heard of it. This was the Apple one that was designed. These delay line or shift register based character displays were another dead end, just like the vector graphics displays. While it made perfect sense for displaying the information to have shift registers in which the characters were constantly circulating around, especially the mix of a short shift register for the row and then a much larger shift register to hold the screen, the problem with this was that you could only update a character once every frame. Now, for glass teletypes, where you had a cursor where you were always inserting things, this is fine. But if you wanted to update more of the screen at once, it was a very slow process. And if you wanted to do something fancier than just print out characters one after the other, you needed to do something else. The solution is a frame buffer, and we'll talk about that next. 1977 turned out to be a big year, not just for personal computer graphics, but personal computers in general. We'll get to that in a bit. First, though, I want to introduce you to the concept of a frame buffer by showing you what I think is about the most basic frame buffer anybody's ever produced. I'm referring to the Pixie graphics display, the 1681 video controller, if you're going to call it that was connected with the Cosmac series of chips from RCA, in particular the 1802 processor. In July of '77, Popular Electronics showed how to use this chip to add graphics to its ELF microcomputer, an 1802-based computer that they had shown over the last year. Now, this was a very primitive frame buffer, even by 1977 standards. 64 pixels across, typically 32, maybe 64 vertically, black and white only. The remarkable part about this is, like the article says, you could do this by adding just one chip to the ELF for less than $25. Like most frame buffers, it presented a very simple programming model to the user. As shown in this grid, 256 bytes of memory are used to represent this 64 by 32 grid of pixels. The first byte represents the first 8 pixels in the upper left corner. The next byte represents the next 8 after those, all the way to byte 7, which is the top rightmost. Then the next row of pixels starts immediately after that at locations 8, 9, 10, and so forth. It's no accident that this is in raster scan order. If you look at the locations in memory, you'll notice that they follow the locations that the electron beam traces out while it is scanning an image like this. To emphasize this further, here the article is explaining how they came up with the Cosmac characters. Each byte represents 8 pixels. The most significant bit represent the leftmost pixel, the least the rightmost pixel of that group. And each bit is set to 1 to indicate a white pixel, 0 to indicate a black pixel. So here they're showing you the first byte is 7B because we have off, on, off, on, shown at the left, followed by DE and so forth. The ELF computer was a study in simplicity. On the left is a wire-wrapped version of the project. On the right is the same project implemented with a pre-made printed circuit board. Remarkably, adding this graphics display involved just adding this white chip at the upper left-hand corner. This is the Pixie graphics controller. Here's the schematic for the project. It's connect the chip up to the processor bus and then hook the video output through some resistors to the chip. This schematic hardly gives us much insight into how this frame buffer was implemented. Let's take a look at how RCA built a similar frame buffer in the Cosmic VIP computer that it was selling also in 1977. For $250, they were selling you this computer that had a little numeric keypad, an 1802 processor, 2 kilobytes of RAM, a ROM monitor, and this simple video graphics display. Here's a photo of it with its case on, and it's interesting. I didn't realize this was blue because all the ads I saw for it were always in black and white. Here's a photo after you remove the case. The big chip on the left is the 1802. The 1861 Pixie processor is just above the silver crystal at the top center of the photo. Here's a schematic of much of the Cosmic VIP. On the left is the 1802 microprocessor. Just to its right is this 1861 video interface chip. And on the right is 4K worth of RAM. Only 4 of these would be populated if you gave them $250. If you wanted more, you'd have to spring for additional chips. Now, the way this has to work is that a byte from RAM has to make its way into the video interface chip, become serialized, and then go out as video. Let's go back for a moment to the memory addresses of the frame buffer. Looking at this, what we want to do is read address 0 from the RAM, get that to the video chip, and then send that out a pixel at a time. Then we want to get the contents of data at address 1, move that byte over to the video chip, send that out serially, and so forth. In these systems, it turns out that the address of the byte to display is the responsibility of the 1802 processor. This is an unusual design choice, and I don't know of other systems that do exactly this. Broadly, what happens is the CPU generates the address of the data that needs to be read, gets read from the RAM, that gets sent over to the video display controller, serialized and sent out. Here's what's inside the 1861. There's not much there at all. The main thing this chip does is shown in the upper right-hand corner. We have 8 bits of data coming in from the RAM off the processor bus that's loaded into a shift register and then shifted out 1 pixel at a time through pin 7 labeled video at the top center. The only other thing we have here, aside from some very primitive synchronization generation circuitry, are some counters that keep track of where we are on the screen and what we should be doing at each point. This diagram shows us what the 1861 does. We're looking at the screen here, and so this is also a timing diagram. Time goes from left to right, then after each line goes from top to bottom. What happens is once a field, just before the display region starts, the 1861 sends an interrupt to the 1802 that should start the display operation. The interrupt routine has just enough time to load the 1802's DMA base address register with the address of the upper left corner of the display. So what we saw before at address 0. Then, while the display area is active, the 1861 constantly sends a DMA request to the 1802 that causes it to read the next byte from RAM and increment the DMA address register. This is the only thing the processor is doing while the image is being displayed, cranking out the addresses. The shift register reads the byte and then shifts out 8 pixels before reading the next byte. This happens 8 times per line, giving us 64 pixels across. At the end of each line, the 1802 gets to execute a few instructions, such as resetting the DMA address to the beginning of the same line to display the line again to reduce vertical resolution and hence memory requirements. Below the displayed area, during vertical sync, and above the displayed area, the DMA request turns off and the processor gets to execute code from outside the interrupt routine, for example, to perform game logic. Thus, the video display takes advantage of a rather unique but rather simple feature of the 1802 processor, which is this so-called direct memory access or DMA controller behavior. Now, to call it a DMA controller in the modern sense is sort of an insult to modern ones. The way it works is when you send a DMA request to the 1802, instead of executing an instruction, it uses the contents of one of its registers, and it has a number of registers, loads the data from the address in the register, then increments the register. So if you hold DMA request down, like the 1861 does, it causes the processor to read an address, put that on the data bus, then read the next address, put that on the data bus, then read the next address, put that on the data bus, and so forth, which is exactly what you need for displaying a frame buffer. In the summer of 1977, the RCA Studio 2 was released. Widely considered the worst video game console in history, it also consisted of an 1802 and 1861 generating 64 by 32 monochrome graphics, 512 bytes of RAM, not even 1K, and 2K of ROM for 5 built-in games. Here's some gameplay from the built-in Freeway game, and yeah, it didn't get much better than this. Let's talk now about the holy trinity of 1977, that is the TRS-80, the Commodore PET, and the Apple II. The Z80-based TRS-80, hence its name, has a 64 by 16 character display. It used a region of 7-bit memory to represent this. Now, it too was a frame buffer and a character buffer, very similar to what we just described. It did not use the Z80 to do the display per se. It had hardware dedicated to that. Each character in the 16-row by 64-column display could be one of two types. It could either be an alphanumeric character that you're fairly familiar with, or it could be a graphics character. Setting 1 bit turned on graphics mode for the character, which would then treat the remaining 6 bits in the byte as representing 2 pixels wide by 3 pixels high regions. This was because the characters themselves were relatively narrow and tall. Each one was effectively 6 pixels wide, 12 pixels high. The graphics mode then gave you 128 pixels wide by 48 pixels high. Rather odd looking pixels, definitely not square, but you could actually draw stuff with it. The Z80 and the TRS-80 ran substantially faster than the 1802 and the Cosmac series. One reason for this, of course, was that the processor was not dedicated to calculating out addresses for displaying on the screen. It had dedicated hardware that would do this, but it was also generally a faster processor. One benefit of this was that you could actually do animation on the TRS-80 and mix text and graphics on the same screen rather uniformly. A good example of this is Leo Christensen's Dancing Demon program. The Commodore PET, also released in 1977, was a 6502-based computer that also had a character mode display. Now, unlike the TRS-80, which had almost a point-like display, the PET only could display characters, but it could also display interesting graphical characters. The display itself consisted of 40 columns, 25 rows each, and each character was square, 8 pixels by 8 pixels. And this made the characters kind of fat and wide, but also made for interesting graphics characters. Here's what it looks like when it's not working properly. But let's take a look now at what it could display if you actually asked it to nicely. It actually has two 128 character fonts in it, and you could select between these with a global switch. You could only display one font on the screen at a time. One of these fonts had lowercase letters, and the other one had more graphics characters. Overall, this whole font is affectionately known as PETSCII, since it looks like ASCII, but has this additional stuff added to it. The result was you could draw interesting graphics with it, although rather limited. The third member of the Trinity, also released in 1977, was the Apple II. It had 3 graphics modes, all based around a 40-column by 24-line text display. The text display used, again, a 64-character font, but these characters could be displayed either normal video, reverse video, or flashing, which was very annoying but made it easy to generate a cursor. Switching into low-res graphics mode turned the display into a 40 by 48 color display. And the way Woz did this was treating each byte of each character as two 16-color pixels. You can actually see this if you switch from low-res graphics back to text. Low-res graphics resides in the same region of memory, so when you switch back to text mode, you can see the way the characters were being used to represent the low-res graphics themselves. The high-res mode used 8 times as much memory as the text and low-res mode. In high-res mode, each byte represents 7 pixels, rather an odd number, but there's good reasons for that, and could be used in an array of 280 pixels horizontally by 192 vertically. This turns into each character in the original character display now has individually addressable pixels. It was some effort for the 1 MHz 6502 and the Apple II to animate such a thing, but programmers figured this out over time. In 1979, Texas Instruments introduced the TI-99/4 home computer. In many respects, this is a bizarre home computer, really much closer to a video gaming console. I mention it here because it had one of the earliest, fanciest sprite graphics systems, which is what we're going to talk about. The TMS 9918 video display processor is at the center of all of the graphics. It had a mix of sprite and character graphics that you could combine to create a full image. TI called the character graphics patterns. And here's how it worked. They gave you a relatively coarse grid, 32 columns, 24 rows. And each element of this grid could consist of one pattern. Think of it as a character A or something like that. Each of these patterns were represented as a list of 8 bytes, and the bits of each byte told us what color the particular pixel should be. Now, what's neat is that each pattern pointed into a pattern color table that would tell us what colors the off and on pixels for that particular pattern would be. Furthermore, the programmer could control what these patterns and of course the colors were, and this allows you to do rather clunky looking graphics, but colorful at the same time without using that much memory. To me though, the most interesting thing in the 9918 was its support for sprites. Now, in the nomenclature of the 99/4, a sprite is a small pattern, again 8 by 8, that could be displayed anywhere on the screen. You could still use the same pattern map that you used for displaying patterns, but in addition, in video memory, you had a so-called sprite attribute table that described where each of these should be drawn. Concretely, an entry in this sprite attribute table looks like this. It starts with a vertical position, then you've got the horizontal position, then you have the name of the sprite. This is actually an index into the pattern table, so this controls whether it's a ghost or a Pac-Man or a good guy or a bad guy. Finally, you've got a color code that tells you which color should be used for the sprite. Each bit in the pattern table is treated as indicating whether to display this color or whether the sprite should be transparent and you should see the patterns behind it. The 9918 supported 32 sprites, of which at most 4 could be visible on any particular line. This is a hardware restriction we'll get to in a moment. The result was that you could make very interesting composite scenes. Furthermore, each sprite had a priority. The sprite number, 0 through 31, indicated the priority. So if sprite 1 and sprite 2 overlap, sprite 1 will take precedence and appear to be in front of sprite 2 when displayed on the screen. This example sort of illustrates it. The tree is in front at the higher priority sprites. Then we have 4 sprites being assembled to make the car. Then we have a few sprites for describing the clouds. Let's look at how the 9918 video display processor actually generated these images. Here's the block diagram from the reference manual or data sheet for the chip. And it's remarkable actually that they're showing us this amount of information. Rarely do you get this level of detail from chip manufacturers. They usually keep it all proprietary and just hope that you can program it. Now this is a lot to take in, so we're going to work from the output backwards. Here in the lower right corner is the composite video output from this chip. And so this is full blast, non-interlaced NTSC. This is being generated by some block here they mark as video logic, and before that we have a color decoder. What that's doing is taking a 4-bit color from this color priority multiplexer and collision detect block that's just upstream. The purpose of this priority multiplexer is to decide, you remember I said that you could display up to 4 different sprites on each line. Well, here they are. There are shift registers, color information, down counters for all 4 sprites on that line. What happens is when a sprite is visible, the information that it is visible is coming from its shift register. And what the priority multiplexer decides is whether the first sprite is visible, and if not, it looks at whether the second sprite is visible, and if not, looks to the third one. And then finally, if none of those 4 sprites are visible in the current pixel, it picks up the pattern. This is the background. Now, as the line is being drawn, the pattern shift register and contents are being loaded directly from video memory according to the pattern table, and this is a relatively conventional character style display we talked about before. The patterns are stored in video memory. The pattern table is stored in video memory. All of these are being transferred by the TMS 9918 from its video memory into the chip as the line is being drawn. What's more interesting is where the information for the sprites come from. What happens is after each line is drawn, the 9918 then consults the sprite attribute table for the line it is about to draw. It steps through as many as 32 sprite entries, and for each one decides whether that sprite is visible on the current line. It does this by looking at the Y coordinate of the sprite and then seeing whether it's in range. If the sprite is in range, then it loads the color for that sprite as well as its horizontal position and the appropriate pattern from the pattern table for that sprite into the down counter, sprite, shift register, and color. It fills these in order based on the priority of the sprites. So naturally the first visible sprite ends up as sprite number 1, the next visible sprite ends up on sprite number 2, so forth and so on. All of this is done before the line starts being drawn. Once the line begins to be drawn, nominally the pattern will be displayed, but a sprite will start shifting out once its down counter, this is just its horizontal position, reaches 0. And every time the next pixel is considered, these down counters are reduced 1, and as soon as they hit 0, the associated sprite shift register starts sending out 1 bit at a time, indicating whether the sprite is solid or transparent. In 1979, Atari introduced the Atari 400 and 800 computers, which had very similar circuitry but different keyboards. This is the Atari 800. The Atari 400 had a membrane keyboard that was resistant to coffee but impossible to type on. Both machines were centered around a 6502 processor running at about 1.8 megahertz and featured 3 custom chips. The Alphanumeric Television Interface Controller, or ANTIC, a DMA chip responsible for processing display lists and sending pixel data to the Color Television Interface Adapter, or CTIA chip, and a sound chip called the Pokey. At the time, most other computers provided a global, rather coarse video mode selection, such as low versus high resolution graphics on the Apple II, a choice of fonts on the PET, and different text and graphics modes with the TMS 9918. A few clever programmers figured out that these modes could be changed during the video field to produce richer displays than was otherwise possible. The Antic chip took this to a whole new level. In the Atari, the Antic chip is responsible for constantly fetching graphics data and memory through DMA. To do this, it follows a programmed procedure stored in memory called a display list, which can be thought of as an extremely primitive machine language program whose instructions are things like display a row of characters and wait for vertical blanking and start again. In a January 1981 article in Byte, Chris Crawford and Lane Winner, two of the designers, explain how a display list can be used to generate a fairly rich image using little memory. Here's their simple image. It consists of a row of small characters at the top, a graphics region described in a frame buffer style, 2 rows of wider characters, and 2 rows of tall and wide characters with a special C. Crawford and Winner show how to instruct the Antic chip to divide the video field into a number of horizontal regions, the contents of which are generated in one of 14 different modes. Here's how they divided up the 192 available scan lines by mode. Here's a list of the various modes and how they're encoded into bytes in the display list. The 4th bit of each byte indicates whether the mode line is requesting a row of characters to be displayed, where bytes in memory refer to characters taken from an in-memory font, or a array of frame buffer-like pixels. These various modes differ on the width of the characters, the size of the pixels to be displayed, the number of bits per pixel to use for colors, and so forth. Here's how the display list is coded to produce the Byte magazine logo. It starts with a special 3-byte mode 7 line command that instructs the Antic where in memory video data starts. Next come 8 more standard mode 7 line commands, then a single row of mode 0 characters, which are 8 pixels wide by 8 lines high, that displays the top line of text. Next come 35 lines of mode 7 graphics data, which displays double-size pixels. This is the Byte logo. After this come 4 rows of mode 1 characters, which are 8 lines high but 16 pixels wide. Finally, there are 4 lines of mode 2 characters, which are 16 lines high. This is the McGraw-Hill Publications text. Note that the C in McGraw is a superscript. This was a user-defined character in one of the fonts. Finally, at the end of the display list is a 3-byte jump and wait for vertical blank instruction, which tells the Antic to send control back to the top of the display list and start displaying the next video field. The CTIA chip takes the so-called playfield pixel data from the Antic, colorizes it, and then optionally superimposes Atari's answer to sprites, which they call player missile graphics. Like the sprites of the TMS 9918, Atari's player and missiles are graphical elements that may be placed at arbitrary horizontal positions, designed for animating small objects on the screen without much effort from the processor. Unlike the sprites on the TMS 9918, players and missiles are tall, thin stripes that extend the full height of the screen. The CTIA supplies 4 players, each 8 pixels wide, and 4 missiles, each 2 pixels wide, which appear in memory more like a fragmented 5th player. Each player occupies a 128 or 256 byte region of memory. Each byte is displayed as 1 or 2 scan lines, and its bits indicate which pixels are solid or transparent. To draw, say, a spaceship at a particular location on the screen using a player, you set the horizontal position of the player's stripe by writing to a CTIA register. The bytes in memory for the player's bitmap should be all zeros above and below the spaceship to make them transparent. The bitmap for the spaceship should appear on the few bytes in memory corresponding to the lines where it should appear vertically. Thus, moving a player horizontally only requires the CPU to update a single byte, whereas moving a player vertically requires the CPU to erase the player's current position and write it out in the desired new one. Here's how player missile memory is laid out. There are 2 modes, one with 1 scan line per byte and one with 2 scan lines per byte to save memory. The bitmap for each player's sprite is either 128 or 256 bytes, although at most only 192 of these are ever displayed. The 4 missiles consume a 5th player region, in which each byte holds 4 pairs of pixels, one for each missile. This means moving a single missile vertically requires a read-modify-write operation to avoid disturbing the other missiles, but this is not a problem for missiles that are only a few pixels high. The release of the Atari and TI computers marked the end of the 70s, and for the moment the end of our story. But, of course, many more things happened in the 80s. So, where are they now? The TI 99-4A, the successor of the 99-4, was discontinued in 1983, although a variant of the TMS 9918 lived on in the Coleco Atom until 1985. Commodore added color and user-programmable fonts when it released the VIC-20 in 1980. It added sprites in 82 with the wildly successful Commodore 64. It added display lists and other graphics acceleration in 1995 with the Amiga. Apple added 80 columns and another high-res mode with the Apple IIe in 1983, went full frame buffer with the Macintosh in 1984, and added some color graphics and a 16-bit processor to the Apple II line with the Apple IIgs in 1986. Atari was hit hard by the release of Nintendo's NES in 1983, but went on to release the Atari ST line in 1985 with 3 high-resolution frame buffer modes.
Recording in progress.
Hello. Do you hear me? Yeah, I can hear you, sure. Yeah, I hear you, but I don't see you. Hi there. Yeah, sure, yeah. Oh, great. Did you manage to start it? Okay.
Testing. Hello? Hello, hello. Is there a mic? Yeah. Hello? Testing. Yep, check and see this. Let's just get you on mic, that way it records nicely. One more moment. Hello?
Microphone ready for the, I'm gonna
Hello?
Okay.
Hey,
they're on me. So they record
And how?
testing.
talk. They're very good here. They got a lot of sophisticated AV stuff.
Okay.
Hello?
And how many people
Hello?
signed up
Hello?
for this
Wait, we can try this one.
class?
You want to really now?
Hello? 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 How about this? Are you comfortable with this, Jeff?
15.
Comfortable holding that?
Okay.
Not bad.
So it would be kind of a party, like for the
What's
best
that?
friends party.
Was that?
I would say it would be kind of a best friends party.
Yeah. Yeah. All right. So audio's good, guys.
Yep.
Video's good. All right, Sergey. Welcome
let me-
to.
A little bit lower. Hold the mic away from your mouth. Yeah.
Welcome to VCF East, 2021. This is 2021? Yeah, 2021. So this is Sergey. How do you say your last name?
Anarin.
All right, so you have the Smarty Kit, and it's very interesting, very interesting. So you ready to tell us about that?
Yeah, sure. So I'm gonna share my screen and tell about Apple One, about Smarty Kit, because Smarty Kit is a kind of a DIY kit to build your own Apple One. And yeah, so I'm ready to start with my presentation with all the details.
I'm here to help.
Okay, so yeah, could you please enable screen sharing for me?
The code, the claim host code. now. Sorry for the wait.
Okay, let me try it. Oh, you're a host now. Okay, yeah, I've seen it.
Yeah,
Yeah,
that should work.
all
Make
right.
you host. Okay.
Okay, thank you.
You're welcome. Sorry about the wait.
Share. Yeah, here we are. A keynote presentation. Do you see? Do you see my presentation right now? Okay, let me remove myself. Stop share, let me new share, just let me stop this share. Just make the one you want, just only with the, okay, let me stop. Yeah, gotta keynote share.
All right, now we see it.
And we got it.
Got it.
So yeah. Yeah, okay, so everybody's in the room, so everybody's ready to listen about this.
And itching to hear all about it.
Okay, guys, let's do it.
Get ready.
Okay, so today I'm gonna talk about Apple One, and I will just cover a little bit of history, and I will tell more about our project, what do we do, and some key results that we have already. We will talk about Apple One architecture and our version of Apple One architecture, and then we would go to the building blocks of Apple One that enables you to assemble them and to get an Apple One working like one that Jobs and Woz has. And so at the end would be Q&A, so you can ask any questions. I would love to answer, because we are just we dived really deep in this topic. Okay, so let's start from the beginning. This week we remember that Steve passed away 10 years ago, and it was a great guy who met Steve Wozniak, engineer, the great engineer, and together they made a really great company, and everything started from Apple One. And I talked to Paul Terrell, who is the guy who was the first to believe in this team and who offered them to quit their jobs and to start producing Apple Ones, because he has seen potential that these personal computers could be really popular among ordinary people, not just the business guys or some special institutions. And so he made this offer to them, and they started to build it right in their garage. And fun stuff was that they planned to build it really just like as a DIY kit for just like $40. But he said, no, just please give it the kind of a turnkey and solution, and it would cost $500 each. And they said, whoa, that could be a business. And so let's have our friends together in the garage and assemble it. And so it was like 1976. It was like only the beginning of computing of personal computing era, and these guys made it all started. And that's why we were so impressed by Apple One and why we wanted to make it the new version of it, because it started a lot of interesting things. So quick facts about Apple One. Yeah, it was like April 1976. It ran 6502 CPU, which you probably know. And tomorrow, I think it would be Bill Mensch, who's one of the creators of it. This CPU was clocked at 1 megahertz, so it's just, if you for sure would compare it with the modern CPUs, for sure it's not so fast, but for that time, for sure it was a really good result. And the very specific fact about Apple One, that it's text mode only, and it's a very popular question: could we play some games, like arcade games on Apple One? And for sure, you can play something like checkers, or when everything is just scrolled for the new frame. But anyway, it's just text mode with 80 chars by 24 rows. And this for sure, it's like big simplification in its architecture. And as I understand, it was done to make it simpler, to be able to produce it just like a normal time frame. And realizing that was for sure wanted to create Apple II, where it's like everything was just really, graphic system was much more elaborated. So what is Smarty Kit? Smarty Kit is a kit of chips and the modules and some extra bags that you're going to show on the next slide. So you get this box, you just like unbox it, and then you assemble it step by step, and in the end you got like really working Apple One. So we have real CPU 6502, we have real chips. We don't have any emulation on the level of logic chips. And we have only Arduinos for video keyboard controllers and for high-res video to out. So that's it. Everything else is 74 series. So it is a really good tool from our point of view to understand how computers work in general, because it's very simple, it's very basic, and it enables you to just kind of follow all the signals, to check all the data sheets of chips and understand how do they work. And so we also have these beautiful bags inside. So our kit is based on breadboards to enable really newbies in this topic, the guys who are just starting in electronics to work with this. Also, we have these jumper wires. Now we work on the more standardized version with the like standard small, medium, and large wires to simplify assembly, like to make it much more Lego style. We have batteries, we have display with the frame, we have electronic components like resistors, capacitors. We have connectors for PS2 keyboard, for connector between CPU and memory, and video out connector, and also video cable for this, because some guys want to connect to their monitors. And we have FPGA cable that is used to update drivers for our Arduino controllers, that is used as video and keyboard controllers. Here's like the render of how it could look when you assemble it. Now we update our instruction and just want to make it beautiful and easy to understand. So we just like model everything right now in 3D. And so just like how it looks in 3D for some of the steps. And here how it looks in color and there is real assembled Smarty Kit. So what is Smarty Kit is a project that we started a few years ago, and recently we've been featured in a video about Apple One by the 8-bit guy. It was really a big thanks to him. It was really cool video, and we have sent him our kit. We presented our kit at CES in Vegas. Guys like Apple Insider, Wired, Italian Version, Cult of Mac, they wrote about us when we were in Vegas, and before this, and it's about 100 kits already delivered, mainly to the US and to many European countries. And we have a big backlog of orders and kits and production that is kind of right now. Shippings are not so fast as we wanted, but just like we work on this, we work right now also on logistics. We plan to sign up for a fulfillment center in San Bernardino in California to speed up delivery, and so hope soon that our operations would be much more efficient than they were before. Yeah, here's some pictures, how it was at CES. Also, we presented our concept and kit to Charles Platt, who is the author of best-selling books and basic electronics. Also, we have workshops in the US, in Russia, and in Singapore. And here's a picture from San Jose school where we draw some pixels, learn that pixel is a kind of a 0 or 1 to on the screen. And today you also can run our board and to make something like these kids did. So you can draw some kind of a rocket or a smiley or write was name just with 8 by 8 ASCII art. So yeah, you can do it by yourself. Our board is already there. You could just run it, press reset button, and just upload VOS face, and then you can just type our code from our online drawing tool, and you're gonna see. Yeah, and so a lot of guys from tech, they already have our kits. It's just John Carmack, creator Quake, you for sure you know him. Daniel Kotke, one of the first Apple employees, Andrew Bosworth, Facebook VP, you've heard recently about him. They've presented these new glasses. It was his team. And for sure, Steve was our first client and he supported us. He'll let us use his code in ROMs. So Steve is just like he took part in our webinar describing how Apple One works. So yeah, Steve was for sure the first and the best. Yeah, here's how it looks in real life. I mean, how do people assemble it? So it's a lot of wires for sure. It's a lot of just like testing and yeah, and so you just, but it's fun. It's for us, we think it's just a fun project. Many guys buy it to assemble it with their kids or nephews, or just like kind of family project, or a gift for their well, for their kids that just like computer science or electrical engineering. And you can see we also have this unibody version. I would call it, because it's just like a simplified one, and it's just like one board with batteries, and you just can you can use it on workshops to kind of engage kids, students in learning more about the first computers, about computers at all, electrical engineering, computer science, and we discuss now also with the top tier universities in the US, using it as a kind of a tool to inspire the freshmen and also the guys who study electrical engineering and computer science in more detailed way, because all of the signals could be analyzed by logic analyzers. They could do a lot of interesting experiments with this, and with software, with hardware, and so just like understand how it all works together. Yeah, so let just like take a look at how Apple One in general looks and how it works. Well, from the kind of a helicopter view, I would say that just it looks just like really typical computer, because just everything is done by a CPU for sure. It works with memory, where it stores instructions and data to process it, and it needs some in-out modules to communicate with the user. Apple One has very simple communication method. It has just a keyboard that works as a kind of a serial, in serial mode. It sends just one char by char, and displays the same. Displays a kind of a terminal. So just like you send char, you get the signal from display that the next char could be sent, and you send a new one. And so it's it is text mode. It doesn't really work like typical graphic system in a modern computer when you have like some video memory where every memory cell represents some pixel on the screen, and just you can change this and then refresh screen in the new frame, and you see the new picture. So the main task of CPU or video processor is just to change these memory cells and then changing the whole scene on the screen. But here it's not. It's very simple one. Yeah, and so the general buses that are there in Apple One is address data, because CPU has like this address to communicate with memory and with in-out modules to address them, and for sure 8-bit data bus, that is main highway to transfer everything inside. Here you can see the kind of our version of this architecture. So we just like also made it a kind of level by level. And so in the center, like central module, I would say central level is like CPU level. And here's like, you can see 3 modules. Like the first one is generator on the left. You can run the like also 1 megahertz like it was in the original Apple One. And also we want users to have an option to run it in a slow mode, I would say, to see how everything is working, because we have tests, our own tests written for 6502 that could be run, and you can see how they are executed, putting some LEDs into the video port out. So it's really fun. You can see it on our YouTube, like how it's done. So you can switch between these 2 modes. So CPU module is very straightforward. Just connect CPU to data bus and address bus. You have a reset button, and you have a sync LED that is emitting when some operation is done. And CPU just like provides 2 signals, RW, just like read write, and F2 just, and they're decoded into just read and write, separate read and write signals that are used then in ports decoder and in memory module. So decoder is very simple. It's just NAND. So it's like very popular chip, and so also building this kit, you can just like get into details how NAND works. Memory module is ROM and RAM chips. They're together because it's pretty much they have a lot of common pins like address and data. And also we have memory decoder that is just like use A12A15 to decode which memory segment is used, and we're gonna take a look on this a little bit later on the next slides. Also, the in-out is represented by 2 layers, I would say. The first one is ports layers, and the second is controller layer. On the ports layer, you see like ports decoder that is just like routes for CPU to connect it to one of the physical ports. Here it's like 3 chips, like keyboard, video, and bit 7 or flex. I would say port for keyboard and video that just like helps to work in this char by char mode. And on controller level, it's just 2 Arduinos in a typical configuration with a crystal, with capacitors and reset button. And they're just like use drivers from, we have open source drivers on GitHub that is just like work with the display and keyboard. Display is video controller uses SPI bus to connect to display controller or to display, and keyboard now we would use our own 40K's custom keyboard, and we're gonna talk about it in more details on when I show it how it looks. So yeah, it's just very straightforward right here. I mean, it's like each level is like, in our case, it's one breadboard, so you can really see it, how it's done. Regarding memory map, in our case, it's 64 kilobytes, and the lower part is RAM, and the higher is ROM. And decoding is done by checking the A15 address line, and if it goes low, so which it generates, it's used to like chip select and output enable for RAM, and for ROM it's a little bit more complicated because we also need a special signal to address our ports, which lay right in the ROM memory address. If there were no any ports in this address space, it would be just very simple. We just need to invert A15 and just connect it to ROM, and that's it. But in our case, we need to use decoder, 3-to-8 decoder, just to connect it to A12, A14, and using A15 as enabling input to work with all the segments one by one. So if we need to connect segment F000, which is the basic one, the first one when that is addressed by CPU when it's just turned on, it is written in microcode inside 6502. So our code, like VOS monitor, the simple operating system, should be there. So the minimum, the very minimum, is to have this one, the signal that will just like routes to chip select and output enable from when F000 is selected. We have electrical scheme also available on GitHub. If you want to just check it after these webinars, you can download it in high res and just like look in more details. But it's pretty much the same. It's like a kind of a sandwich with many layers, kind of a big burger with a lot of ingredients. So you can just like check it and see it. That it's very simple. We have also a lot of capacitors. It's like decoupling ones, just to make this power more stable, as you probably know. Yeah, okay, well, what are the building blocks? What are just like these bricks, Lego bricks that you really use to build your own Apple One? So in our case, is just for CPU, it would be WDC 6502. The one that is produced by Bill mentioned his company. So we use them. It's very good that it's CPU, it's static, so it just like can stop at any clock, and just like in it's simple, it's a single step and so on. And we use this crystal generator like for 1 megahertz and 555 for low rate clock, and also we use this NAND gate to decode a read-write signal. for memory, we use 65 to 56. For ROM, we use like 65 kilo ROM to make it simpler when you program it, because for sure we can use 32 kilos for ROM, but in this case, if you write some program, you assemble it, you compile it, and you got this machine code with some addresses. If you're gonna load them in this ROM, you just wouldn't see the exact addresses, because right now you can edit segment FF00, and you just like it would be right the same addresses as CPU reads them. If we would use 32 kilos chip, it would be much harder to program it and understand it, which is like with this relative addressing mode. For 3 to 8 decoder, we use 138 is just also classic, the really classical one. And for this, we use like 3 inputs for A12, A13, A14, and A15 is used like the enabling one. Because if A15 goes low, in this case, this memory decoder would output everything high, and so it would mean that ROM would not be selected when the RAM is addressed. Output ports, in out ports, we have like this out port is latch register as a video port, because when I want to latch char code, ASCII code of char that needs to be sent to display. We also use either register, just simple register for a keyboard port, either shift register to simplify connection to make it serial, not just parallel. And we're gonna discuss it when I take a look at our keyboard. We use a buffer just that with output enabled pins for the bit sound port. When it's addressed, it just like transfers the flag pin from video or keyboard controllers right to the D7 data bus pin. And we use this 4 to 18 decoder as ports decoder, where we just like as inputs, we have 2 lower addresses like A0, A1 to address ports, because they all like have numbers like D10, D11, D12. And also we add read and write signals to combine them to have signals that specifically read some port or write to some port. And it is easier to have this decoder instead of some extra logic to make some ORs or NANDs or ANDs or some logical operations for signals. We do everything right inside this decoder. Regarding controllers, it's just Arduinos with this just using classical, I would say, code to work with the video controller, but we needed to make it speed up it, so we have used the basic driver for such a displays, but we needed to put everything in one file and to speed up this SPI connection to speed up the scrolling, because basic scrolling was very wasn't very fast, and we need to work with this because otherwise it looked really strange. Keyboard controller can work in 2 modes, I would say, with the 2 versions of drivers. One is for PS2 keyboard. It supports it. It's a very simple one. And the second is our own 40 keys keyboard, where it needs to do much more work, because it needs to scan all this keyboard to find the key that was pressed, and then using the table decode it to ASCII code, and then send it to keyboard port, and then CPU can read it. Display is just like assembled from from a standard one, but we need to convert it to 3.3 volts. So that's why we need a lot of resistors. And so we use special module to do this. And also it has frame to look nice because in basic it has red color. It doesn't really look cool when it's red. So it supports this text mode. It has scrolling, and also basically it supports also touch screen. We have experiments with a touch keyboard, but many users with whom we discussed this, they said that it's cool, but kind of it's not really Apple One spirit to have a touch screen keyboard. So it's better to have real keys, and we have one. Yeah, so we created this one. Now we kind of updated it a little bit to support for this automatic production with the SMT, and but it's pretty much like this. So it's 4 rows, 10 columns, and keyboard controller needs to scan this rows or columns. It doesn't really matter, just like how you do it. But anyway, you just like need to scan 0 or 1 and check in which row and which column key was pressed. Then you need to check shift if it was pressed too. You need to save it, and then you use table to convert the kind of it's kind of index and array, so you convert it to ASCII code to send it to CPU, because CPU for sure and it works with the ASCII codes. And yeah, it was kind of fast, but it's pretty much how it works and how it what we do. So would love to answer your questions.
Do you want me to ask him? All right, Sergey, we have a question.
Sure.
Can you put this in an empty Apple II case?
Yeah.
And use the keyboard?
You can put it inside the empty Apple II case and connecting keyboard. Because as I remember, Apple II doesn't, it's like it has a built-in keyboard like an Apple One, and so it uses the special connection, doesn't have any PS2 interface. So in order to do this, you probably would need to have some converter that could be used to use it as a kind of a keyboard for Smarty Kit.
Okay, yeah, that makes sense. It's not straightforward. It's a little complicated. Okay, makes sense. Does anybody else have any other questions for Sergey? Yes. Are there any extra features that you get by using new parts as opposed to original vintage parts? Any new features?
Yeah, sure. Yeah, I mean, basically we use like one RAM chip. It's much simpler. I mean, when you do assembly, and the cool stuff about, for example, video and keyboard controllers, that now you can just like have it kind of as a, I would say, laptop. Because you have like display right on the board, you have keyboard to just like stick together. So it's a new feature, I would say. You can just like have your have it portable. The original Apple One is just like, you know, it's a keyboard and the big monitor that you can transfer it, but it's just you need a kind of a power supply. In our case, you just need batteries. And also what's cool, and what yeah, because mainly what we use as new ones is just these controllers and one memory chip to simplify everything, and the rest is like it's original. I mean the 74 series for all the logic, original CPU, the new version of it. I mean with the static mode, so you can just like, as I said, the main feature that you can run it at low clock or stop it, just like making step by step, which is cool for education. And the rest is like very genuine, I would say, and it has the features of original Apple One, I would say.
All right. Any more questions? Yes. What are the inputs in for it? So it's like the original Apple One. What are the inputs for it? Or is there, like, to put a program? Does it have a cassette port, for example?
Yeah. In our case, right now, it's like we have like built-in programs, right, in RAM, like this pixel art and some Hello World programs. For sure, can burn some classic software like BASIC right to the RAM using programmer. Yeah, we tried to make a kind of a serial interface from computer, so you can just like emulate key by key pressing of the keyboard and just like repeating the code, was monitor code, I mean, to populating memory cells. But right now we don't really support this. We just use built-in programs. We can support this in a keyboard driver, so we can open Arduino development program and then just change the code, to burn it to as a part of a driver, and then when you press, for example, tab that button, it just like would load it also char by char, this program that you want to have. So we have questions, yeah, about this cassette interface. For sure, it's possible because it has this all the signals. It has this memory decoder that addresses C000 memory segment that was used for cassette interface. But I would say it's a kind of a special challenge for guys who would love to have this. It's possible. It's not. I know even now I understand how I can do it, but we have much more questions about the assembly of this one. I mean, to run VOSFace program, for example, and stuff like this. And so we're just like focused, spend our time on making our instruction look like a legal one. They can sit and do it much more than developing this cassette interface. So I think we're gonna make maybe some challenge, or I would say a kind of a hackathon to guys who would love to compete in making something like this. I would say to have this cassette interface.
Okay. Are there any more questions? All right. Looks like that's all the questions, Sergey. I appreciate it.
Okay. Thank you.
You're welcome. Thank you for showing this. It's very interesting.
Thank you, guys. Yes, so please follow us, subscribe to our email list, clone our code at GitHub, and for sure watch our videos on YouTube. Would appreciate that. If you can drop me a line if you want to know something special, or just say thank you, well, just please do it. Drop me a line. I would appreciate this. Yeah, for sure. It would be cool if you could run it and share some pictures. Yeah, how you do it, because it should be simple. I mean, you just like turn it on with a switch on top right. It start printing like Made with Love by Smarty Kit.
On. Oh, yeah.
And then
showing,
you press
it's
reset.
showing Wozniak.
Yeah,
It's
we got it.
the Apple, what is it, 30th anniversary demo?
Yeah.
Oh, there
Yeah,
you
that's
go.
it.
I didn't see that before. That's pretty cool. And then it'll just cycle through the different ASCII art of Wozniak and then Jobs. All right, I've seen that before. Okay, that's pretty cool. All right.
Yeah.
I'll let them see that if they want to. Thank you, Sergey.
Thank you.
All right. Have a good day.
Yeah, thank you guys. Have fun there.
All right.
Bye.
Bye.
Testing, testing. Microphone testing. Oop, I shouldn't do that, huh? Okay. Testing some more. Hello, welcome. Is there a projector?
Oh, let's see here. Did it go to sleep?
Ah, yes. And my glasses. Maybe I'm not. Okay. Try not to mumble. Bright lights. Yeah, 5 more minutes.
So you cranked up to 2K, it looks like there's some artifacts on the screen.
I am. Thanks. Thanks for suggesting. I am.
It's probably trying to downscale.
Yeah. Good idea. Let's go to like 1080. Huh. Maybe one step further down?
I think the resolution of the projector is fairly low.
Okay. I'll just keep stepping down, see what works. Not so good. 1440, 1050. What do you think the ratio is?
I guess if you try to do like something 69.
59.
16 to 9, sorry.
Oh, 16, 9, yeah. So not that. 16:9, maybe?
Projectors are 4:3, but the screens is 16:9.
Oh.
So it's like overshooting, but most of the people have been running widescreen content.
Any suggestions on getting rid of that artifact?
Or the noise?
Yeah, or that's just noise?
Yeah, I think it's right here.
Yeah, I was talking about the worms that were crawling across there.
We think it's because of the projector. We think it's the projector. Yeah. We don't see it on the screen where it's split.
Uh-huh. Okay, well,
Close enough.
That seems a little still, I can go for a bit. Yeah, all right, let's try this. What happened? Huh. Did I close my browser? No, nope, not that one. No, not that. This one. Ah, that's better. Okay, so if I do this, how's that look? Oh wow, it's really showing. Okay, one more time. All right. All right. So I guess I'll get started here in well, maybe I'll just get started. I thought I'd start by celebrating today, and we have all of our friends and other people of similar interests, and I thought that was very special. You know, it's kind of a quirky hobby, or, you know, niche, so to speak, and you know, you know, I'm very grateful that we're able to get together in person and also virtually, whoever's watching. And and then also thanks to the organizers and volunteers who have spent countless hours doing all the good things that they do to make this event possible. So thank you, everybody. All right, this one's about FUZIX, and I guess a little bit about me. I'm a lifelong learner, interested in programming languages, operating systems, and a little bit of hardware. Specifically, I like the Zilog Z80 stuff, Z180, and in particular, Motorola 88,000 class stuff, and everything else that's old. So VAXs, PDP-8s, everything here is pretty much interesting to me. So that's something. And when I'm not doing computer stuff, I do tree climbing and rock climbing. And I'm also an amateur radio operator. Recently, I've been doing HF, FT8, and JS8 call stuff, which I find it fascinating. So, what is FUZIX? So, first of all, let me just say I speak with no authority in this matter. I'm more like a tourist. You know, I had a little project earlier this year, and I've known about FUZIX for a while, but you know, had a chance to dive in a little further, and I'm basically going to speak sort of like a travel log. So I went there, did that, and this is what I saw, and this is how it was, and you know, it was a lot of fun. So check it out yourself if you're interested. So FUZIX is a Unix-like operating system for small systems, and by small we mean pretty much an 8-bit processor with, however, not a small amount of RAM, but a large amount of RAM for 8-bit, which is to say, like on a Z80, the minimum's thought to be around 128K, which means, you know, there's going to be banked memory stuff. On a 6809, it's said to be perhaps possible to get everything running in 64K. I've never tried it myself. It's built like the older systems, the older Unixes. Basically version 7, system 3, and some system 5 bits. It honors POSIX, so it's not really what's called heritage Unix. It's more of a modern interpretation of a Unix-like operating system that runs on a Z80. So it is currently in active development. It is, it's written by, or it was started by a guy, hold on, I can get to the history. It was started by Alan Cox, who is a retired Linux kernel maintainer. So he was, you know, he knows his Linux, he is Unix, he's a very prolific programmer, and he started this back in 2014, 7 years ago. First commit, and since then it's been in active development by a number of people. And there was a milestone release of 0.3 in the August 2019 timeframe, and we are currently in what's called pre-0.4, which is to say that, you know, I guess when Alan's ready to you know, formalize the interfaces, this is what really the version number is about. To publish sort of an interface that says we're not going to, you know, we're not going to break this for this version. When he's ready to do that, I guess we'll get 0.4. Stepping back a little bit, here's sort of a list of some of the systems that were mentioned. The list is actually much longer than this, but I picked out a few that, you know, that might mean something to, well, they meant something to me, so I listed it. So there's the Amstrad, there's the Dragon 3264 Tandy Coco 2, which is to say the 6809 machines. There's Memotech, which I've never seen myself, Microbee. I happen to have a P112, which is, I think it's called Digital Design P112. It is a Z180 with a meg of RAM and a couple 4 serial ports. It also has the GIDE, which was sort of an IDE interface back in that time. This was 2006, I think. So in my case, I have a compact flash attached to that. It also goes Sinclair ZX Spectrum, Tandy Coco 3. I know the Tandy Coco and the 6809 development seems to be pretty solid. And then TRS Model 4, 4D, 4P with 128K RAM, which I think my interpretation of this is that that's sort of a stock configuration without any additional hardware or whatever. Then there's Steve Cousins, you know, series of single board computers, SC108, 114, and other various, you know, Z180 or Z80 machines, boards, and RC 2014. In that configuration, there's a bunch of, yes?
Would there be anything for, you know, bank switching, CPM type systems, generic S100?
If you can do bank switching, there is a chance that that it can be made to run. Yeah. So on the Z80 front of things, if you can bank switch, give or take, with, you know, a total of about 96 to 128K minimum of RAM, you can probably make it work, or it seems like that's possible. RC 2014, there's various different combinations, and there's a guy that on YouTube that demonstrated FUZIX, so I think that's also covered. And then there is the 68K, so I think active development currently on Ataris, as well as the tiny 68K board, I think. And then recently, just earlier this year, there was one for the Raspberry Pi Pico, and also for the ESP8266 kind of stuff. So, so we did the history, and we could talk a little about the features. And yeah, so if you're interested, I'll put up a link to the GitHub, but you can take a look at the you know, the systems that are listed, comments about that. There's been an ongoing, can this be done on Apple II discussion, and you know, as of recently, there was some kind of new discovery that, you know, maybe with some additional hardware, people are going to make it work. We'll see. Some of it has to do with also, I'll mention later, but the compiler. So let's just touching on the features. My personal favorite #1 feature is that it's small enough to understand. So I've built Linux systems, NetBSD, OpenBSD, FreeBSD, all those. You know, I've gone through the sort of this the official steps on, downloading the kernel source code or the system source code and, running make files. And, I've built systems, but, I've hardly ever understood really what was going on. I can read C code, but it's just so much C code that it's sort of never really tangible. Whereas this system, I felt like there isn't that. There are hundreds of source files, but it's not really thousands of directories. So it's really, I don't know, 20 or so directories. And so it gets complicated because of the different processors support and the different system support, which, it sort of necessarily makes the whole thing a little more complicated. But if you just limit your scope to the system and the processor that you're in, it's more tangible. Anyway, technically it can do multi-user, with multi-serial port. It can do multitasking if you have a timer source. It does run without a timer source, but it still kind of expects to have like a keyboard interrupt. It does implement signals, and it does run without the memory management unit, which, initially I was kind of surprised about, but when you think about it, the earlier Unix machines didn't have the MMU support, so, it's not too crazy. And that also sort of contributes to the potentially smaller and simpler implementation. Also, I guess, sort of you're limited in what you can do. You do have that, the issue where, a poorly behaving program in user space could, of course, trash the kernel buffers and whatever else and crash the whole machine. But, that sort of goes with the territory on the 8-bit processors, and that's that. Some processors are better supported than others, and the Z80, Z180, 6809, 68K seem to be, actively, there's a couple guys that are tracking Allen's changes and making sure that they, continues to work on their system. Allen seems to be focused mostly on the Z80 side of things. I have seen, but I mean, it almost seems like he has one of everything, but his attention seems to be mostly on the Z80 stuff. Recently, there's a guy named Dave Givens that he's contributed the ARM Cortex M0, which is the Raspberry Pi code, Raspberry Pi Pico, and the ESP8266 stuff. And there's also the 6502, 8088, PDP-11, TIMSP 430 stuff, but they are in, I don't know what state they're in. They are there. There is support for TCP/IP. TCP/IP uses various different sort of these cards that are made to, the cards have Ethernet on it, and I guess it has its own processor on it, and they're meant to sort of interface with embedded controllers and whatever else. So it has a simple interface that mostly supports streams like TCP, and one of the products is called WizNet, I think, WizNet 5200. So that's sort of how TCP is supported. I have personally not tried it and don't know how well it works, but it's there, and I do hear about people doing stuff with it, so I guess it does work. I think what they do is they run a daemon that talks to those, the Ethernet offloaded cards, chips, whatever they are, and sort of brokers that to the other process. So it's not TCP/IP as we know it, but it's not TCP/IP as it's implemented in Linux or Unix, but it's sort of TCP/IP that works for the 8-bit processors. Okay, so yeah, so this is the part where I talk about my personal experience. 2020, 2021, so that's about 8 months ago, maybe a little bit more. A friend of mine, Crawford, we picked up, we both had one of these MSP 430 boards, and I guess there was a blog post on a website called Cowlark, Dave Givens' website, that he made that FUZIX run on the MSP 430, which is like an $18 card, embedded controller card. It's the processor number is the FR5969. It has a 64K of FRAM, which is more or less flash, or how should I say this? It's non-volatile RAM. Well, I guess that's what it is. You can turn the power off and the RAM value is still there. Sort of, it acts like flash, but there's no complicated flash protocols. You just write to it, and it's there. And you turn the power off, it's still there. Turn it back on, it's still there. And anyway, so got one of those boards. We wired up a SD card to it, and I had FUZIX. Well, actually, this was a little more complicated than that. So we downloaded the tools. We built the kernel. We built everything. Well, actually, the kernel didn't even build from the latest code. And then that's when I discovered that there's a little bit of bit rot. So we went back to the day that Dave Gibbons actually committed the code. That code downloaded and compiled after we figured out that we had to roll back the compiler to the compiler that he was using around that time. And then we had we built the system, we ran it. It ran well, it did stuff, which is to say that, you power it up, it boots through the kernel, it gives you a login prompt, you log in, which is at that point, init has completed running and it hands off to a shell. It's a very minimalist shell, but it does the usual. You type in a command, it finds the executable, it loads the executable, it runs the executable. If you have a pipe, it'll pipe the output to the next program, and so on and so forth. That sort of stuff all ran fine. I spent then the next couple of months trying to get that code base to actually compile and run with the latest code, and didn't quite achieve that. In the end, I ended up, I guess in that time frame, which is, I guess, a couple years had gone by since that time, and the kernel actually had grown in the amount of memory it needed for itself, and it basically, I couldn't fit it into what I had on the MSP 430 at that point. So back to the drawing boards on that one. I would have to, get further down and figure out how things were going to have to work. So after that, we sort of put that aside, and I have a P112, which I've not been doing anything with for many, many years. It's one of my favorite boards. I have a story to tell about this board. So several years back, I actually accidentally applied 12 volts to it, and it didn't boot. So I kept doing stuff, and eventually, it's bad news, right? 12 volts. Eventually, the flash chip popped. And that's when I realized that, OMG, I had 12 volts instead of 5 volts. And I was very sad, really sad. And very angry at myself, so I put that aside. I couldn't even look at it for months. So several months go by, and I worked up the courage to actually desolder all the chips. Well, some of them are socketed, so I took the socketed ones out. I desoldered the main chip. There were two main chips on that board. One was the Z180, and the other one was the Super I/O chip that had the multiple floppy, the printer port, and 2 serials, or whatever. So I desoldered both of those carefully with quick chip, whatever that alloy is. And I learned to do some surface mount stuff. I found the replacement parts, put it in, and I replaced the other parts. I had a guy help me with this. His name escapes me. He sells Z80 boards on the internet. But anyway, I managed to actually put it back together. So that's the happy ending on that board. I've been looking for something to do with it, so here it is. I got FUZIX to compile and run on it, and that's the board that I brought this weekend. So it's over there. I have a table I can demo, and love to talk to you about FUZIX if you want to come by. So, one of the reasons I'm doing all this vintage stuff is that I like to learn, and all this is a learning experience. And so here's what I learned. I learned I didn't really understand makefiles until I actually had to work with a makefile of that nature. So I learned a whole bunch of things about makefiles and linker files and all that stuff, building systems. Learned more about how the Linux kernel, the FUZIX kernel which is to say, it builds the same way as any other kernel, I suppose. So I learned more about that. That was kind of fun. I learned not everything's working. Just because it's in the repository doesn't mean it compiles. So that was, not a surprise, but more of a challenge. Maybe I can get it to work if I fix a couple things. And sometimes, it's a motivation for, wanting to understand what went wrong. I gained a lot of skills in traveling in time in the repository Git. We rolled back to certain dates. Does that compile, link, run? Sometimes it does, and so you mark that, and then you sort of move forward a little bit. So we did a lot of that kind of exercise, which was kind of educational, very educational. So I learned about really the constraints in these sorts of systems would be the memory, and so for example, the Z80 and the banked memory system, it turns out there is wild variation of how banked memory was implemented. By and large, they fall into categories, but if you enumerate the permutations, it's bewildering. But there is some amount of code already in place and some amount of documentation that describes how you could, if you wanted to, bring this all together and sort of either customize it for your system or see how it works. It's a lot easier on the other 32-bit and other sort of more flat, simpler memory architecture. But for the banked systems, there are combination of factors where, depending on which part of the memory map is banked, whether you put the kernel above it or below it, and what do you do with the parts that are banked, and those sorts of things. So I was going to actually talk in more detail about that, but the presentation didn't quite work out, and I don't think it's going to be that interesting, or I can't present it in an interesting enough way. So I'll leave it at that. We can discuss more if you come by the exhibit. I learned a lot about the compiler dependency, or the operating system's dependency on the compiler in order to bring the whole system together. Initially, by the way, FUZIX was sort of modeled after or built on top of the previous operating system called UZI 180, which was written by another guy. And back in that time frame, it did, in fact, self-compile, or you were able to build UZI on a CPM machine, or whatever hardware you're running on. You could. Well, it was assumed that it was a Z180 machine, but you could build the whole kernel and the user space from CPM, and then write it to a partition, and then boot that. That was, from what I read, it seems like that was possible, and but that's no longer the case. FUZIX at this point clearly assumes that it's going to be cross-built from either Linux, Mac, Windows, some other more modern environment, I guess. And for the Z80, the official compiler is the SDCC compiler, which is also currently in active development. It's a Z80 pretty modern C standard compiler that produces, from what I understand, pretty good code. It is very slow, and it's very resource intensive. I have, a fairly modern i7 or a Ryzen system that still has to grind through it to actually to build. Whereas the TI, I was using a GCC compiler, and that, relatively speaking, that was much, much faster in producing the final product. So, and SDCC also has its limitations. This is sort of not many other people are sort of compiling an operating system for it, so they don't actually support some of the, the memory banking models, or doesn't produce the C code work smoothly with the banking model. So there's some patches that people had to make to do that. And then, some thought experiments. At the end of the day, you only have either 32K, maybe sometimes more of space for the user program, and that's really kind of tight. And if I was to want to compile a C program that needed more than 64K RAM, what do I do? So maybe using a compiler that can produce overlays, or having some kind of overlay mechanism might be interesting, possible to make things better. So that's about where it wraps up. I have been thinking about what I would do potentially to contribute to the project some more. One of the issues that came up was that the developer experience isn't quite that great. You sort of have to really know how to put together the development environment yourself. They do mention, and most people seem like they're running Ubuntu 20, and so there is a guy that's producing the packages, SDCC, with the patches in an Ubuntu repository, so that's great. And if you're familiar with that, that's all fine. If you're not, then it's a little challenging. So I thought maybe I could build potentially vagrant boxes, or some kind of mechanism for distributing the whole entire development environment, so that people can just download it and run it, so that they're in a, they download the run, they check out the source code, and they would be in a position to compile and test out the code. Something like that I think I can do. Potentially, I think the project's always in need of documentation, more documentation, or even sort of curating the documentation, because it is lots of code and scattered all over the repository. And I also have a couple other Z180 boards that I'd like to spend some time potentially trying to port. So that's that. Yes. So in doing all this, I did find I did spend some time trying to figure out where the people are. So if I needed to, where are people discussing things, and I found that there isn't a mailing list. There is a mailing list. It's right here listed, and I have it linked from the resources page. But not a whole lot of discussion happens there. Some. Alan himself has a Hackaday page. If you go to Hackaday and search for FUZIX, you'll land on his page, and that's where. And then the most of the real discussions seem to be happening in the GitHub issues themselves. So I actually have never seen this in a project, but that seems to be the case. So I had to turn on all my notifications for the repository. I got, and then I started seeing the chatter a little bit. So. And finally, I wanted to give a shout out to David Givens. He has a YouTube channel that has, this must take a lot of courage and probably also a lot of time too, but he basically sits down and he starts writing code, and he's talking his way through it, and you get to see him do all of this. So these videos are like 4 hours, 6 hours long, and they're like a dozen of them. Of course, that goes with, there's a lot of noise to sort through, but I found him actually educational. I think he probably does embedded development for a living. So he knows his compilers, he knows C, and he's been doing it for a long time, and he just, so he goes through stuff, and I usually go through it and watch it at a higher speed, but I do stop and rewind and slow it down, and so anyway, so his YouTube channel is over here, and that was I hesitate to say I recommend it, but if that's the sort of thing that you can deal with, then definitely check it out. There's and I was looking around for something to talk about as well. There's one guy that's written a MIDI player, I think, and he targets FUZIX. So I don't know why. I don't know. I don't know what else he's doing, but I did find he's a Japanese guy that had a Twitter or something post. So thought that was interesting. And that's it. That is my presentation. I'm here to answer questions if I can. Go ahead.
Is FUZIX really, the purpose is to learn about an operating system, or would it have any advantages over something like Chromix or NPM?
Right. So one of the things that would be different is the hierarchical file system. So you get that. Do you get that in NPM? I know you get multi-user stuff. Multitasking, but do you get the longer file names with the paths anyway? So that was one of the things that was mentioned. Yeah. That's a good question.
I mean, Chromix was modeled after Unix, so it might be a closer comparison.
Yeah, I'm not terribly familiar with Chromix, so I can't answer to that. As for NPM and CPM, I think one of the advantages would be you're programming in C and you get the whole sort of the Unix API, but also you're cross-developing, so it's not the same. For me, it was all about learning how things work. So yeah, go ahead. Yes. So the question was to describe again the compromises that were made to fit everything onto the smaller system. Sure. So let me go back to the, I don't know if I mentioned it, but the definition of small, I had a definition of small somewhere here. So the definition of small is basically 8-bit processors with 128K RAM. For Z80. I think there was some mention elsewhere that, or somewhere that I read that it might fit on a 64K if you're on the 6809 processor. But the compromises are, the features are fairly limited. You have files, you have processes, you have libraries. You don't have, any dynamic loading, so no, what is it? No shared object. So the object format is very simple. It just loads. There is, as it stands today, there is no anything that takes advantage of the position-independent code. So, and Z80 doesn't even have that. So, so you're limited there in that. The compiler actually needs to help you, sort of write the code, and there is no fix-up or load time, anything about the binaries. So, so that that part's sort of really simplified. There is what else is missing? There's no floating point, none whatsoever, and what else? Other than that, I mean, there are pipes, there's processes, there's signals, and there is swapping. Yeah, so I forgot to add to that definition of small that you need. It really sort of assumes that you have some kind of disk and block device disk. Today, it's most common to have SD cards. So there's a machine-independent SD card driver written in C. And I have a compact flash, but that's another alternative that seems to be popular. Yeah, so it'll probably fit on two. So what am I trying to say? A kernel plus, maybe not all of the utilities would fit on but a small set of utilities would. Subset of the utilities will probably fit on a floppy comfortably.
3.5-inch high density.
Yeah, 3.5-inch high density, yes. I didn't mean the lower density ones, but yes. Yeah.
Can you talk a little bit about what David actually did in his video presentations? Because I think I found it fascinating as you did.
Yeah.
He live coded.
Yes, he live codes stuff. In fact, maybe I can just bring up his YouTube channel. Was it? I think his handle is like HJalfie. Yeah. Okay. So and then here is how do I do this? Playlists. How do you find his playlists? Yeah, so he has a playlist of here the 8266 stuff. Unfortunately he doesn't have it for the Raspberry Pi. Oops, didn't mean to play it. I just want to get to the list of them. And this is number 13. So he's got like several of these, and this one's an hour and 40 long. So he starts with setting up the tools. And he compiles a small binary to make sure that he can sort of send that down to the I guess he's working on a card, and then he really builds his way up to getting the whole thing to run. So and he goes through basically all his usual tricks and tips about how to verify each of the steps on how things are working. In the particular case of the 8266, it's complicated because some of the code / what he wants to use as a library is already on the chip, and so he needs to then work with that and be able to call it. But when he calls that code, he needs to set up the registers and the memory sort of just right, so that the code is sort of expecting or can find what it's expecting to find. So he does that. He goes back and forth with the compiler. He disassembles the stuff that he writes to verify that it's working, and he just sort of builds his way one step at a time up through all of that. And it really takes like, I think there must be like 40, 50 hours worth of footage. And some of them, there's a whole session where he just sort of, things just don't go well for him. But he's recorded through it, and then he comes back the next day saying, okay, I did a little more research, that didn't work out, these are probably the things that I did wrong, and so we'll start from that. But then he goes through and so he builds the kernel, he tests the kernel, he builds the user land, he tests the user land, he makes sure that the kernel can start the user land stuff, and so on and so forth. So it's pretty extensive. In fact, I haven't watched through all of them myself, but parts that I did watch were and he does edit some stuff, and some of the parts where he's just waiting to compile, he just cuts out, and he just like 2 seconds later it's done, and he's testing it. So anyway, I believe he does the whole port of FUZIX in these 13 plus videos. So. All right. I have a table. I will be here all day tomorrow. I'll try to spend as much time at the table as possible. And I'm leaving kind of early on Sunday, so I won't be around Sunday afternoon. I do have two Z80 boards for sale in the consignment area. One's a SB180 by Steve Ciarcia, featured in Byte magazine whenever it was. It was a classic. And then the other one's a BCC 180, which is from Micromint. It's also a classic. But anyway, that's it. Just say hi if you want to talk more about this, and or if you're a fan of the Motorola 88,000, because I'm looking for 88,000 friends. All right. Thank you very much. Nice. How long did I go? Half an hour? 45 minutes, maybe? Can you unplug me, please? Thank you.
Recording in progress.
Right now? All right. Can you hear me? Sir? Closer? Is that too loud? All right. All right, so we're just waiting for her now.
Recording in progress.
Space, the final frontier. There was a lot of feedback, so it's like space. The final frontier. Yes, I can. Who's speaking?
Oh, hold on. I gotta switch.
Oh, hey, there you are. So how many people?
1,000 people. Someone else asked me that. They're thinking, oh my goodness, is anybody gonna be watching my thing here? You want me to count? Really? You want to count?
Is there more than 5?
There is more than 5. Keep going.
25?
I'm gonna say about 25 to 30. Yes.
Okay, good. So
Yeah.
I'm not gonna speak to myself for an hour.
Yep. All right. How are we doing, Ethan? All right. So welcome, Stephanie, to Vintage Computer Festival East 2021 here at Wall Township, New Jersey, InfoH Science and History Museums. You're going to be talking to us about implementing a simple VGA controller with FPGA. And you've had a lot of other videos and Zooms before, but I'm sure there's going to be fresh content now that it's been a little bit of a while since you've been at East and even West, right?
Yeah, well, today it's going to be pretty special. This is the first time I'm doing it, so it's going to be interesting, and there's a lot of stuff to cover. So I hope people will find it interesting, and thank you for having me again this year. Hopefully next year we'll be able to see each other face to face.
Yeah, next year we're going to do April 29, 30, and May 1st. So,
Nice.
It's 6 months away. Hopefully, things will be in a better situation where you can easily come from Canada. Because I know, a lot of people from other countries really couldn't very easily come here or at all. So I'm hoping it'll be more people from around the world, because we used to have people as far as Australia, some years. So
Cool.
it'll be nice if we could have that again.
Yep.
All right.
Awesome.
So you ready to start?
Oh yeah, I'm ready. I've been ready for a while now. So
all right.
hopefully the crowd is ready. We're gonna just go breeze through a lot of stuff, and can you tell me, do a show of hands to see how many people have done FPGA stuff before?
All right, let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9 people.
Okay, so how many out of these people are pros?
How many are pros? Crickets. Nobody's a pro.
No, okay, cool. All right. I'm not a pro either, so that should be fine.
All right. So do you have, I guess you see your screen, so you have all full access, so you're pretty good to go right now, right?
Yeah. Do people see my screen now?
Say it again?
Yep. Do the people see my screen stuff right now?
Yes, they do. They see it on
Is it clear?
Yeah, everyone's clear to you? Yeah, it's very clear. Very clear.
Awesome. Great.
Yes.
All right.
So I'll let you go, and I can just stay here in case you want any moderation or anything like that.
Yeah, please, if there's anything along the way that is really unclear, please, people, stop me. I tend to talk, and I don't see the time pass. If for some reason my microphone goes off or something, although I don't think it's going to happen because I switched my microphone, please let me know. But so if there's an emergency, anything, just let me know along the way. If people have questions along the way, please stop me. It's kind of always a good thing to stop to break the tempo and just to take a breather. Otherwise it should be fine.
All right, you're good to go.
Thanks, Jeffrey. All right. So do I see, can I hear everybody? Can you say something so I can hear you? Okay, awesome. Thanks, guys. I don't see you, so it's very weird for me.
I can try to turn it around. I don't know if let me see.
Yeah, a view of the crowd would be nice. Awesome. This is great. Yeah, hey everybody, it's awesome. Okay, great. All right, so I want to move quickly to the agenda. So basically today, well, first of all, my name is Stephanie. I'm a hardware design engineer. I've been doing hardware design engineering since, well, for the last 30 years, I suppose. I've tried to start many companies in the past. When you start your own companies, you know that you have to learn a lot of things. So along the way, I've learned to do mechanical design and FPGA design, which I started doing when I was in LA. It was back in 2010, so it's been a while. Although again, most of my knowledge I've learned, you know, over time on the heap, you know, from a lot of people, you know, self-taught type of thing. So I don't use, well, I'll talk about that later, but overall, you know, I've been doing a lot of electronic design for a long time. So I guess I should be in good position. I've done a lot of video stuff. That's always been my thing. I just love pixels, the potentials of pixels. It's not like people like some people like telecommunications and packets and stuff. I find that stuff so boring. So basically today what I wanted to do is, in a nutshell, introduce you to the whole concept of the whole VGA stuff, which is really the first part will be about getting into the timings and the pixels and dot clocks and all the theory behind the creation of an image. And then we'll get, the second part will be into going into Quartus, which is the software I'm most used to, and it's pretty easy to use. I didn't create anything in advance, so we'll just create everything from scratch. So if it's something that might be good enough for people to start getting into the FPGA design, I'm going to do it in Verilog, which is really close to C. So it should make the idea of people getting into it maybe might be a little bit easier. So we're just going to focus on creating the signals we need to drive the display. And then at the end, I will go back into explaining how you would implement the rest to interface to memory and then get pixels out for a video DAC or a DAC, whatever video DAC you have in mind. But at least you have the understanding, know how to go about the next step afterward, because I think within an hour we cannot you know, go through everything. There's two possibilities I'm going to talk about at the end, which is really to implement the controller to drive some memory to do bitmap display or a text display, which are two very different ways to go about displaying information on the screen. Let's move on. So like I mentioned, the goals, just understanding how video works, the different parts we need. I'll go into Quartus a little bit. I'm going to surf over a lot of things. I'm going to talk about a lot of things. I'll try to put a lot of focus on things that are really important. Again, if there are questions at the end, please come back to me. I mean, worst case, if you have more questions later and you're really interested to do it, then you could come on Discord, on the FUZIX Discord, and ask me questions directly to answer your problems or whatever. I'm more than willing to help people start doing Verilog and stuff like this. And usually when people get on board and doing it, then it becomes a lot easier over time. The challenge of FPGA usually is not to get started or to get stuff compiled. The challenge is then when you're starting having very dense devices and when you start dealing with you know, clock domain crossing and stuff like this, which is really the bulk of what makes a good FPGA engineers. And after all this time, I'm still not even super comfortable doing all that kind of stuff, but I manage. You develop some techniques over time. But so I was asking for people in the crowd, how many people are good or have touched FPGA. So maybe half or, you know, 1/3 or whatever. Well, not 1/2, but anyway. So I just want to let people know that since I've learned everything on my own, I kind of developed my own technique or own ways to implement the code. And for some who've been doing that forever, been to school, maybe it's not up to par to their understanding. And so I don't want to offend any gods of knowledge, or people that have a strong belief in how it should be written. Software people tend to be like that sometimes, but even within the software realm, software programmer realm, there's different technique or ways to write stuff. So let's not, worry ourselves with that kind of stuff. But I just wanted to say that in terms of writing Verilog, I'm doing it in a certain way. Might not be the perfect way, but I think it's better, it's easier to understand. And when it comes down to create a Verilog, not a creative Verilog, but create a core to drive a VGA screen, even in that case, there's many ways to do it. I'm going to do it a certain way, and it might be good, might be bad, but at least it works. And I think at the end of the day, that's what we want to do. And then we can make it better if we want, but the deal is really to make it work. I expect people to not be, for the people who have not done any FPGA, to not have done any, possibly not have any FPGA experience with Quartus or anything like this. So that's why I thought it would be a good idea to just, go from scratch. And this is a recording people will have.
I don't hear your audio. Can you check to see if you're on mute? Oh, I think maybe some people think it's because your microphone, maybe you adjusted the microphone, maybe a cable came out. And try to, you're on mute right now, definitely I could see. That was your video.
Okay.
All right,
good?
there you go. Now I can hear you. Okay.
Sorry,
good.
it might happen again, so please do the same. I'm really sorry. I don't know why it does that. I thought the microphone was the camera was the problem, but apparently it's the system is the problem. So I'm sorry about that. So I don't know where I was, but anyway. So again, I want to go quick with this. So I've learned a lot of things over the years. I'm doing things my own way, like anybody who's learning their own thing on their own pace at their own time. They tend to go into a certain way of doing things. Today, I'm going to use Quartus 18.1. It's the software that is free. This is the web edition. Xilinx called them the web edition. You just go until you download it and you register, you download it, and you're good to go. I think they're probably at 21, 22 now. I stick to older version because they usually, the more recent version usually don't cover the old parts. Nowadays, it's a good trend to use older parts because they're more available if you go in China. If you want to use the latest and greatest, it's very difficult. So there's no point into downloading anything more recent than 18.1, but suit yourself. I will use Verilog today because it's simpler. It's like C. Like I was mentioning before, there's 20 ways to implement a video signal generator. So I'm going to be doing one. All right, so how does a display work? I'm sure everybody came across that kind of information, but let's assume you did not. Overall, within an image, there's a blanking period, a vertical blanking period where back in the day with the screen, there was the electron, moving around the screen to display. Sometimes it was on, sometimes it was off. There was a time where the electron gun needed to go back to the beginning and start, displaying the screen again. So all this stuff stayed even in this era of digital and everything. So basically, the way on the left, I don't know if it's your left or your right, but on my left side, the white drawing shows that the display time where the pixels are actually shown on the screen is what starts the frame. And then there's the blanking, the horizontal blanking, which is really the time where normally the electron gun would go back at the beginning and then start. There's a sync pulse that tells the system, hey, we're at the end, so let's start again. And there's the same thing for the vertical time, which in that instance they put at the bottom. That configuration never made any sense. Okay, are we back? Oh my God, I hope it's not gonna happen 20 times like this. But anyway, so let's, so don't want to spend too much time on this. My mind always it made more sense to have the overall presentation of the image display, the other side, which is basically when you start at 0, 0 at the top left corner, you're in the blanking area. And then you're going to stay in blanking, you're going to come across a V-sync, H-sync every line. And then at some point after the 45th, we'll go through the timing after that. But at some point, the display, the display enable, the blankings are both disabled, and then the display starts, and then you can start outputting the data out for the video DAC to see your pixels. So like I said, I'm going to stick to my presentation, but again, suit yourself. The concept is always the same. It's inverted, but yeah. So first step when you want to display an image is basically just find out, okay, with an FPGA is really, okay, what are the timings, when the pixel needs to be on and off, when do I need to create the sync pulse, the vertical sync, the horizontal sync, and when the blanking needs to be on and off for the vertical time and for the horizontal time. So I found this great page. I'm sure some of you in the crowd knows about that page. It's called thetenyvga.com. That guy just put all the timing information for most of the old standards, and it's a great source of information for anybody who wants to do any video stuff. And so I really recommend it. I never found anything better than this. So moving on. So for us, we need to find out at first how many pixels there is in line, how many lines there is in the image, including and excluding the blanking, and when specifically do we need to create the horizontal sync and the vertical sync. So we start with the duck clock. The duck clock is really the time that the pixel will stay on and then move on to the next pixel. So with the VGA 640 by 480, this is really what we're doing today, is at 60 frames per second. We're talking about a clock, a standard clock of a 125 megahertz, which is about 40 nanoseconds. And during one frame, the overall frame will last 800 pixels long for one line. And there will be 525 lines overall. I forgot to put the information. Anyway, so 525 total lines, which amongst those 525 lines, there will be 480 lines that the pixel will be enabled, and there will be 45 lines that won't be. So that means that there's literally, well, there's in the design we're about to go through, there's 3 signals we'll have to create. Well, at the beginning, there will be 4. The time we'll have to enable a signal that says, hey, we are during the blanking time, the horizontal blanking. Then there's a signal that says, that's going to say, hey, we're during the vertical blanking. And then there will be a signal that says, hey, we have a horizontal sync to create, and then we'll have a vertical sync to create. So that means overall, at first, we'll need to create 4 signals out of the 25 megahertz clock. And at the end, we're going to combine the vertical blanking and the horizontal blanking together. So this is the signal that will tell our circuitry to display or not any pixel at all, or enable the counters or stuff like this. So that's basically how we do this. So in the FPGA design, what we'll do is separate, there'll be 2 separate sections. The first section will be the horizontal section. I don't know if I had to put it there. Yeah. In a nutshell, you'll have a pixel counter that will count the number of pixels during a line. And when at the end of the line, when you reach the 800, then you'll return to 0 and start counting to 0 to 799 again. And that will increment the line counter till the line counter reaches 525 or 0 to 524. And then the whole cycle will start again. So here I created this flow which gives you an idea how we'll go about. So there's the main counter here, which is the pixel counter from 0 to 799. And we're going to instantiate a comparator that says, hey, between 0 and 160, we're in the blanking period. So that means that we're going to get one signal to go high. And then when we're higher than 160 or 160 and higher, we're going to go back to 0. And we're going to do the same thing for the sync, which is when the pixel counter becomes higher than 15, because if I go back, the timing says that the blanking, if we look at the page here, the front port, which is really just before the sync, you're going to have 16 pixels before the sync will last 96 pixels. And then you have 48 pixels left over before you start the image. The same thing for the vertical, but instead of counting in pixels, we're going to start counting in lines. So for 45 lines, I think 45 lines, we'll have to generate a vertical blanking. And during that vertical blanking, we'll have to create a sync, a V-sync, that will last 2 lines. But before, we have to wait 10 lines, and which means that we're going to start at 10, and line number 10, and we're going to finish at line 13 or less than 13, which is 12. So, and then there will be 33 lines that nothing will happen, which, by the way, is always a great time if you have a CPU or any system that drives your memory. It's always this is a great time to transfer your data, because you don't need to access your memory at that time. That's the best time. Well, basically the time you need to transfer your data is while during the blanking. But a vertical blanking lasts a long time, so it's great and it's very, the size of the time, it's very known. It's very easy to implement. I mean, the vertical horizontal blanking is known as well, but since it doesn't last that long, it's a little bit more tricky to manage when you have a lot of data to transfer. So personally, I usually use the vertical blanking and just transfer everything, and then I just wait for it to come back. But anyway, I'm digressing here. So to come back to the pixel counter, to create the sync. So like I said, so pixel will have to wait before the pixel counter reach the 16. All right, we're good. Yeah, I'm just disconnecting the microphone, connecting back, and we're good. So we'll do that 2 or 3 times again. All right, so pixel counter, I'm sure you're getting the pictures. On the other side, for the vertical sync, it's the same concept, but we're using lines, numbers instead of pixels. So same thing, from 0 to 45, we're just going to make sure V-blanking is 1. And for the vertical sync, we're just going to monitor the line counter to be between 10 and 12. And when it's reached that point, then it gets to 1. All right. So at this point, we'll go through a microglossary for Verilog for references. So basically, when you're using Verilog, you need to create modules, which is a block of circuitry. And to start or to create modules, usually you describe the different types, which is 3 types: input, output, in and out in terms of direction. So these are the key words that we would use. We'll use them later. We want to express numbers. Try to remember you're very down in the logic chain. You're very at the bottom. So everything is you always have to specify the number of bits you want to use, and then you do a colon, semicolon. My English is, I don't remember this one, apostrophe. The letter B for the value, it's a binary, of course it's 0 and 1, but then you always have to, if you say 16 at the beginning, it means the number of bits that's going to follow. It's the same concept for X. It's H, the number of bits that you want to implement the number in. It's more obvious with, it's more obvious or less obvious, I guess, with decimals. Okay, well, thank you for letting me know. I'm going to zoom and move around. Okay, so for the numbers, same thing. So, you know, with the decimals, in that case, for example, the 4'D, it means I want to encode the number 11 in 4 bits. Here, the same thing, 128, I want to encode it in 8 bits. So this is an error that we tend to do sometimes. You're going to say, hey, I want to put the number 256, and you say, hey, I'm going to use 8 bits. When in reality, 256 is really 9 bits because 8 bits is 0 to 255. So you have to be careful. Although I guess most Verilog people will use X and binary more. That's what I do. I rarely use decimal, just for comparison, stuff like that. It's easier to read. To give you an example how we create a module, usually you're going to say the word module and then you're going to give a description name. And it's always great to store the file, like the Verilog file you're going to create, to have the same name. So it's a lot easier to track later. And this is one of the examples I was talking about before, where this is one way of doing things. I like to put everything on one line, because in Verilog, you can, usually what people do is that they say input the name of the net that comes in the module, and then later they're going to say, hey, this name, like for example, I would say, hey, this is wire video clock in, and it's like you're redefining the thing to say, hey, that input is a wire. It's not a register, it's a wire, and so on and so forth. I hate that way of doing things, because if you want to find out if it's an input, not an input or an output, but if you want to know if it's a wire or it's a register, it's an output or an input, it's not as obvious. That's one of the reasons why I took the habit of always putting an underline. It's not a Verilog thing, it's a Stephanie thing, to always describe the input output. So in one view of the code, you can say, okay, this is an input, this is a wire, and it's a lot clearer to do it this way. Well, I think. And this is the same thing for the output. The output, you can either create them as a wire. Wire is simply a connection, or you can say, hey, it's going to be a register, and which means that the output will be coming out of register instead of a combinatorial logic, in a nutshell. These are the amount of bits that you're going to carry for that specific value. It's a vector. You decide, okay, that vector, that signal, carry 4 signals with it. You can do it for outputs as well. So this is really how I do it. And that's why I'm making an accent on this, because this is really, I don't see that way of doing things very often. I adopted that way because, like I said, it's a lot easier, one read. I don't have to go back in the code and look it up and what is it. And it's, when you're playing with other people's code, it tends to be very annoying. And so basically, module, name of the module, parentheses, you describe all your signals in and out of the modules, then closing parentheses, semicolon, I guess, whatever. Then you write all your codes. That's what we're gonna do next. And then at the end, you say end module, and you save your file. So finally, the keywords wire, reg, assign. Assign is really a way to do combinatorial logic. I'll show you later. Always, it's to create a block that will be driven by a clock or not, depending, but I'm not going to touch the blocking stuff today. I'm just going to do non-blocking. The if case, you'll see it resembles C very closely. There's case that we use a lot, because one thing, and I'm going to talk about this right now, is the concept of, for people doing software, migrating to hardware, people have always a hard time, because the concept is, people need to understand, is that everything happens at the same time. Every time the clock ticks, everything moves. It's not like a serial thing, one line after the other. And so in order to make sense or to create events, we need to do a lot of state machines, and you do the state machines with case and end case, and we do them, I do them all the time. So this is important to wraps your head around, is the fact that every time, everything happens at the same time, or every blocks are always blocks will be activating something or doing something. They might be in one state and just being idle, but every clock cycle counts. That's why FPGAs are so great, because you can get can have many instances of the same thing in different state doing many things at the same time. So one interesting to know. So let's move on. So vectors always expressed by the biggest number first and then the 0 later, or it can be a portion of like 3 and 2 and or 3 to 0. You take sections of the vectors. You can concatenate your different signals with different bits to come into one bus, and you can define that bus and say, hey, so that helps create different organization or addition or multiplication or division. It's very easy to do it this way. Arrays, you can do arrays by saying, hey, I want a register. It's going to be 8-bit containing bytes. And the nomenclature for arrays is a bit different, where you start with 0 and then you say the numbers you want. In that case, you would have 4 registers of 8-bit. Probably not necessary today, but I thought I would mention it. So when you want to instantiate modules within another modules, you literally say the name of the module, and then you give a new name for the instance you want to create. And then you describe by a dot the name of the signals. In that case, I forgot to put the I. And then you create a new wire or the same name. You say, well, clock signal, which is defined somewhere in the upper level of the Verilog modules, because it's always one modules within another modules within the modules. And I could instantiate many Stephanie modules by saying module Stephanie 0, module Stephanie 1, and so on and so forth. And then you connect all these things together. So this is the overall, the module, stuff that we use mainly in Quartus. So what I'm going to do now is just migrate to Quartus setup. Hold on, I'm going to make this more important. Hold on, there you go. I hope you see clearly. Okay, so, all right. So I'm going to, so do you see clearly, or I need to make it bigger? I don't know if I'll be able to make it bigger at this point. That thing doesn't scale very well. Is it better now? No, probably not. Okay, okay, let's see. I'm going to start a new project. Oops, no, that's not what I wanted to do. So new project wizard. It's not very easily scalable, although maybe I could scale the, okay, let's see if this works better. Okay, okay, so you don't, okay, so unfortunately you don't see, let's see if you can, do you see the wizard? Okay, I'm gonna switch back later. Okay, so this is the wizard, I'm sure you see clearly. So with Quartus, that's the Prime Light Edition 18.1. I'm going to go somewhere else. You know what? I'm going to stay there. I'm going to make it really simple. I'm going to install it VGA. The next step is to create an empty project. There's nothing to instantiate. I'm going to use a Max 10, which is really nice. I'm going to use a very small device. Usually, the Max 10 is the FPGA that have the flash internally to program the device, which is really cool. I'm going to use a very small device, the cheapest device you can find. I'm going to use the 10M202, which has 2,000 gates, which is more than we need. This is typically 144 pins. So, you know, like I said, I don't think we need to worry ourselves with the number of pins today. Like I said, the basic here is really to create just the core. So normally what I would do, so the system has created a project. So the first thing I would do is to create a, you go into, am I back into the thingy? Yes, I am. Okay, cool. So a new a Verilog HDL file. So it creates a .v file. So I'm going to put the microphone a little bit far away so I can see what I'm doing. So module we're going to call it VGA. I'm going to start opening. So first thing first, we know that I'm going to assume that the system has a reset input. So I would say input, I'm going to declare as a wire. So it's just a connectivity thingy. I'm going to say reset, and I'm going to put _E to say that's an input. I'm going to assume that the system is going to provide me a clock, which is going to be the 25.125 megahertz on one clock pin somewhere. Then I'm going to say, well, there's nothing much more that I can do than right now to say, I'm going to create a HSync out. I'm going to create an output VSync out. Whoops. Underscore out. Then I'm going to create, I could either create a H blanking out. Well, you know what? We'll do it this way. So H blanking out. I'm going to create a V blanking out. And a name that is used a lot with DAX and everything, it's DE for data enable. And data enable is really the combination of the two blanking. But if you would want to drive other part of the circuit with the blanking, this is something you'd like to have. The two separate signals can be very useful for other stuff later. Something else is also very useful is to get, and this is where I should have let a little bit more space. So I want to get the pixel counter out for other modules to share, because sometimes it's useful to, so actually I could define it as a register in that case. So I'm going to declare it as a register. So I'm declaring a register, it's going to be 12-bit register, and we're going to use it as a counter. So I'm going to say pixel counter, and I'm going to describe it as an out. I'm going to do the same for line counter, line count _O. And well, that's it for us, I guess. Since we don't have a lot of time, we're not going to do any memory interface, but like I said, that's a good start. Okay, let me see. Something I wanted to say is that we talked about the number of pixels during the line. So there's 800 pixels. So to round up to 2 exponent something, so the closest is 21024. So that's probably why I think it's 9 bits, 10 bits. I'm going to reduce it to 9. And we spoke about 512 lines, which is 525. So the closest is 1024. All right. So the first step is in order to create what we want is to create the counters. So we start with an always block, and this is the syntax. We're going to say that we want the block always to react when the positive edge of the clock will come in. So we're going to use the clock input here. Okay. The way the Verilog stuff begin, it's not accolades, it's a begin. It's always begin and end. You replace all the accolades with begin and an end. I'm going to implement a asynchronous reset, because you could include into this parentheses other condition to be respected for the action of the always block to be executed. A lot of people do synchronous reset, which means that you would do something like that. I do asynchronous stuff. I don't know why. It's a habit. No, the reset here, sorry. So you could do something like that, and then the always will be executing. So in that case, so these are the signals that you want the always block to activate. So there's other techniques, other ways to go about this, but this is very typical. So what I do is I say reset here. Whoops. All right, so reset my ASS. So begin, end, else, begin. This is very typical to start an always block. This is, you get used to it. You say, okay, I'm going to create the first counter. I'm going to say pixel when reset, say that it's going to be 10 bits. That's also a way I'm doing things. You don't have to put the separator, but I find it it's more clear. So this is a non-blocking statement that says when you get a positive clock, when the clock is passed, the value will be stored in pixel count. Good? Okay, thank you. So it's when you're doing, it's called a blocking or non-blocking. I always mix them both, but anyway, which means that every time when you use this way of expressing the assignment, it's always happening 1 clock later. Okay, so if positive clock happens, it's going to be effective the next clock. Okay, so keep that in mind. It's very important. So it's literally like a value will be transferred after the clock has passed. So you can assume that the clock that follows, the value has been assigned. All right, so so what we can do is say pixel clock, if pixel clock is smaller than, let's say we're gonna do the 800, so we say the value D800, which means that we have posted the value 800 in 10 bits to make it equal with the pixel counter. If it's smaller, you say, I'm going to put a big in here, and you're going to say pixel count can you hear me? Okay, I can keep talking. I can do a song and dance if you want. So, yeah, sure. Okay, so basically, okay, great. I'm sorry. Okay, is it clearer now? Hold on. I'm going to, there you go. Okay, well, cry every time that happens because I don't notice it. So you're my monitor. Okay, so to recap, so what I do here is the always blocks, every time there's a clock happening, the block gets executed, okay? The reset is 0. That means that I'm in this part of this if statement. And if pixel count is smaller than 800s, then I'm going to increment it by 1. Okay, so the counter is 10-bit wide. I'm just going to get 1 plus 1 plus 1 plus 1. But if it gets to 799, which means that it gets to the point where the counter exceeds the if statement, I'm going to say, okay, reassign the counter back to 0. Okay, so this is as easy as it can get to create a counter with Verilog. It's very straightforward. And we're going to do the same thing for the line counter. So basically, this is the pixel counter. Okay, I'm going to separate the always block. You can have 1,000 always block if you want, but in that case, what I'm going to do is use line counter, line counter, line counter, line counter. I'm sure, do you see it clearly? I hope you are. Let me see if I can go away. There you go. Okay, so same thing, but we're going to change the value here, 525. So I'm not sure if what I'm going to do is perfect and it's going to work, but it's a way of doing it. And there's always time afterward for people to try and to debug it. I could put, so because right now we have created, actually I did something wrong. Because now I'm assuming that every clock cycle, the line counter will increment, which is not true. In reality, it's a big boo-boo I just did. Okay, so let's fix that. You know, I just drank my own Kool-Aid. So what I'm going to do is bring this here, which means that every time, okay, hold on, am I doing this right? Yes, okay. me recap everything. So these are nestled, I think this is the word to use, counters. So what I do is I count pixels to 800, and when I reach 800, I go back, I go in this section here of the bottom section of the if statement. Let's see if I didn't forget anything. Yes, I forgot here. Begin. And this is the begin. This is, I think it's okay now. Okay, so I'm going to put back, I'm going to reset the pixel count back to 0, but then I'm going to increment line count by 1 till I reach the count of 525, and then I'm going to go back to 0 and the whole thing start over again. So nestled, you know, counters, two counters, but one is predicated on the ending results or reaching the value of the first one, and so on and so forth. That should work. Now what we have to do is, first of all, we need to create the condition, or we need to generate the H-sync signal. By the way, depending on the resolution you're using, if you want to go faster, there's the polarity of the sync that changes. So something you can invert later, but I'm just letting you know that vertical sync and horizontal syncs for monitors are not always activated by one value or, you know, high value or something. So what we want to do is say, hey, I want to create the H-sync. What I'm going to do is say, I want to create an H-sync every time the pixel counter is, so this is really combinatorial logic. And what we would do is say pixel logic is equal to, or like an if statement. So pixel counter will be, I don't remember the value. Can somebody tell me the values? Okay, it was like, okay, hold on. I'm going to go back to check my pixel, my information here, my presentation. Okay, so I said, okay, 160, and it lasts 15 to 112. Okay, so bigger than 15, so 10 be 15. So this is the first condition. And you want it to end like any if statement in C. And you say smaller than, I said, 112. So 10-bit wide count value with the value 112. And you can put parentheses here to complete everything just for the sake of better understanding. And you use a interrogation mark. It's like a if. Do you have that in C? I think you do. And you say, you could leave it that way, but for clarity, what I usually do, I write down also the values of what it should be. So when this is true, this value is assigned to H-sync. And when this is not true, this is the value that is assigned to H-sync. But normally, since it's like a condition, it's implied that if this is true, H-sync would be 1, and if it's not, then it would be 0. But like I said, I tend to use, I put everything for clarity because your brain doesn't have to think. Your brain is already busy doing something else, so you don't want to bother yourself with that kind of stuff. So H-sync, so basically all the signals are creating the same way. I just used the line counter and the line counter here. And I go back to my value. It's supposed to be 9 and 13. So VSync will be created when line counter is bigger than 10, bigger than 9, and smaller than 12. And like I said, when this is true, VSync will be 1, and H-sync will be 0. So the blanking, same thing. I'm going to do a copy and paste. I'm going to just move that up for you people. Blanking, same thing. V blanking, same thing. You assign. And the values for this is, in that case, pixel count should be minus 160. And we're in, you can do sign and unsigned stuff. It's assumed that if you don't specify it, it's going to be unsigned. So, and signed stuff with Verilog is a bit tricky. but just to let you know, be careful when you're doing signed stuff with Verilog. And the other one is minus 45. So minus 45. Okay, I want to move my ASS quickly. I'm running out of time. So 45, same thing. And ultimately, the signal D0 here would be a combination of both. So it's or H blanking or. So if you would use, there's this analog devices part ADV71 something. They use all these, you know, if you wanted to use, like you wanted to do TMDS stuff like VGA with DVI or HDMI, those converting controller or these VDAC or whatever, they use this signaling. So HSync, VSync, and DE. And DE is basically to tell it when the pixel data is valid. So you create these two signals and we're done. So normally I would store it like, well, I'm going to store it there, I guess, I suppose. And normally you would, to finish this, you go in File, because you created a file. I think okay, automatically, when you say new Verilog file, it assigns automatically the file to your project. And normally I could click compile. It's going to, on its own, assign the pins. And there's ways to, oops, something is wrong. There's a way to force the pin to tell it to, there's an N somewhere missing. Probably somewhere here. So in NF bit is and else. So one big N, anyway, I don't want to waste too much time because I'm running out of time. But so there's like an N missing somewhere where I put an extra one, which should not be there. So for people who want to do FPGAs, super important. The best strategy to create a big circuitry and everything is usually to do your circuitry before you do your PCB. You compile your design when you're sure that you're pretty much there, but most people just do half of it. They do the PCB and they finish it later. But it's always a good way, it's always a good thing to let the tools assign the pins for better connectivity and fastest delay and for things to go as fast as possible. And then you lock your pins and then you do your PCB. But sometimes the signals are all over the place and it just makes your PCB design really crappy. So usually you're going to do the other way around, which is to assign to tell the FPGA, hey, my pins will be there because it makes my routing easier. So this is in a nutshell what you would do to just create the signals. I want to go back for the last part of the presentation where I'm going to show you in terms of block diagram, how you would go about, oops, that's not what I want to do. Save, yeah. Okay, so moving on. So you see my, okay. So my couple of slides left I wanted to present you is how you would go about implementing this into, so I'll try to make it as big as I can. So there's the block we just created. So let's zoom in here. So there's the generator that we have just created. We have all the counter that we needed. Few things, okay, this is the text. So I'm going to go back to the bitmap. So normally with a bitmap, it's very simple. You use your pixel count to drive the memory, okay, which means that every time the pixel goes from 0 or the way you do it or the way you can do it is really to just use the pixel line. If you have a lot of memory, you just assign the pixel count to the address to the memory. And also you add a circuitry to move your pointer to a new place in the memory every time you want to start a new line. So basically you could use the line count multiplied by the number, like for example, let's say you want to display 640 pixels, but in your memory, you want every line to be contiguous, one after the other. You use the line counter, you create a small circuitry in Verilog, and you just, it's a multiplier. You say line count multiplied by the 640, and it gives you an address, and you would add it with the pixel count. So every time you pixel count to 0 to 100 to 800 or 640 in that case, you would just add the multiplication with the addition with the pixel count, and then the pointer would move to one memory location to the other. Something you need to keep in mind. So usually the memory that you need is very big, so you would need to drive an external SRAM, for example. And then depending on the color depth, then you put more data. So you could have like a 32-bit and have a RGB. Something you need to keep in mind is that the memory always take a certain time to get the data out, so usually 1 clock. So you need to delay everything by 1 clock, so everything happens at the right time here at the DAC, so otherwise everything will be off. So the binary implementation or the bitmap implementation is very easy because it's straight up just a counter driving a memory. Whatever comes out, you get out on the DAC side. Could be a 1 byte, and then you could put another memory block, which would be a lookup table. And from that lookup table, you could get a 24-bit output from the 256 value coming out of the main memory. It's really up to you at this point. The second implementation is the character set. Let me zoom out. So same block that we created today. And then it's a bit more, it's interesting because it's definitely more complex because you need first the memory to store your characters. So the ASCII you would want, oops, sorry. The characters, so the text memory, that you could also combine with a color memory, which is like a little bit like the Commodore 64, I suppose. So a separate part of the memory, which for the same location, but a different, I mean, in the memory, they're different 2 banks, separate banks, but with the same offset. You could have 1 character information, which means the ASCII character, and 1 byte that goes along. That's, for example, that's what I did in the Phoenix. There's 4 bits for the foreground, 4 bits in the background. What you do is then that character drives the character ROM, which could be inside the FPGA, that you assign a file to a RAM block and you say, this is my ROM, character ROM. And the first 3 lines will drive the line of the character you need. So if you have the ASCII character A, you need to scan between which line you want of the character A, depending on where you are in the display. So obviously, if you're line 0 to 8, then you need to have the right line for the right line you want to display, right? Makes sense. Then the second part needs to be driven by the choice of the character you want. So if the character said ASCII 41, then you need to go get the data for the character that is the 41st character. Yeah, that's it. And then through the 41st character, you scan the 8 lines of the character. And within that characters, there's the 8-bit. And then you, depending on where you are on the line count, the pixel count. So this is the easiest way to do it anyway, because when you're starting to do 9 and 16 and all these things, not anything that is not a 2 square or exponent something, you can use the pixel count, which is 0 to 8, and then you pick I said pixel shift, but in reality, you choose the bit you want. So you want to display the first most left bit first, and then you move on to the second one. And so that bit value tells you, is it a background pixel or it's a foreground pixel? So basically, are we displaying a pixel from the letter A or not? And then can control the switch here that decide, is it the foreground color I want or the background color? And then you have these value can be RGBA, and then you go out to your VDAC. That circuitry takes a little bit more time, so you need to delay those H-sync, D-sync, and D accordingly for the DDAC. So ultimately, when the first pixel comes after the blanking is over with, everything needs to be perfectly synchronized perfectly for it to be seen. Mostly the DE signals is the most important. If the H-sync and V-syncs are offsetted, sometimes it's okay. Monitors are not that very picky about this. So that's basically it. So I'm 2 minutes away from being done. But yeah, that's overall how you go about creating a VGA or any other resolution, just changing the size of the counter, And depending on the pixels, the line, and so on and so forth, and the polarity of each thing in VCF. So that's it for me. Do we have any question at this point?
As you write the Verilog code, how do you iterate over verifying it's correct?
Okay, so basically verify it's correct. So it's like a school of thought. There's this idea that, you know, you can, hold on, I've lost my screen. Anyway, okay, so normally with Verilog, there's a way to simulate the circuitry. You can create the test vectors. So which is it's a Verilog file with extra instructions to create, you know, signals, stimuli on different inputs and outputs, and part of the software allows you to see what's coming out. Functionally, it's something that can be very helpful. I think the strategy is usually, if you're a good soldier and you want to do these things right, you usually just going to spend a lot of time creating all these stimuli in test file, and you're going to test it on can test it on modules, you can test it on the overall projects. But when you start dealing with bigger blocks like DRAM controller, big controllers and stuff like that, it becomes very difficult, takes a long time for simulation to happen. Honestly, I, for one, I'm not a simulation person. I hate it. It takes a long time, so a lot of overhead. I'm more a practical person. So I would literally compile it and put it in the circuitry and make it work. And then when I'm starting to have, early on, when the FPGA is very empty, you met your timings really quickly. Unless you do it in like really fast, high-speed stuff, you don't have to worry about anything. You just put it in there. You make sure that your pin are you assign the right pins, the right signals are driving the right pins, and you start debugging it live. You can also use a block that you can instantiate within Quartus that is called a chip. Well, I call it a chip scope. It's called ILA in Quartus. It's a block that simulates a chip scope, like a logic analyzer. Well, that's why they call it ILA, I suppose. Intel logic analyzer, whatever. And so what I do is I call it a chip scope because Intel calls it a chip scope. Anyway, instantiate it, you say how many inputs you have, and then you have another application you connect to the JTAG that allows you to monitor what's going on. That's how I go about it. I use all the internal JTAG accessible tools that allows me to probe the circuitry inside the FPGA through the chip scope circuitry and everything. I'm not a simulation person. Some people love it. I hate it. It's a lot of time. So that's how you go about testing it. But you get used to your thing and you realize that when things are not working right with the chip scope and everything, you figure out your problem really quickly. And then things get more tricky when you have timing issues and everything where you start analyzing, but usually stability. But this is for another class, another day. Does that answer the question? Anything else? Oh, every time you compile, like for example, we have 2000 gates. Well, I'm calling them gates, but it's LE logic element. But anyway, it's always been this thing with Xilinx and Intel. It's never been really precise. But anyway, to answer the question is that at the end of the compile, there's always a statistic page at the end. So it tells you how many resources you've used, how many block RAM you've used, how many PLL you've used in the device, everything. It tells you everything. You have a summary at the end, so it creates a page with summary, and there's other documents that gives you all the rundowns of what happened and what they're using and when and how. So it's pretty precise. But you know, if you manage to get your part full, by the way, a good rule of thumb for anybody doing FPGA design, don't exceed like 70, 80%. Anyway, if you go higher than that of utilization, you start having a lot of issues and timing and stuff like this. It takes a long time. So it's one of those things that you can never reach 100% usage, but yeah. So take a bigger part and make your life easy. Does that answer the question? It's a great question. None. You know, the Cyclone 10 is in reality a Cyclone 4 with a smaller geometry of fabrication. There's nothing new under the sun. The Cyclone 10 didn't introduce anything new. I mean, they changed a couple of names for certain blocks, but it's same thing. I got the same. Actually, this week I was debugging stuff and I compiled both, and I end up having the same exact results. So there was no difficulty at all. Even the parts have the same pinout, aside of 2-3 pins that are different. It's the same, and that's funny because I realized that 3 months later that the pinout of the packages for the Cyclone 10 that I was using, which is a 40,000 gates, was exactly this, almost the same. 3 pins are different. So Cyclone 10 is really a respin of the Cyclone 4 and probably like, I don't know, 180 nanometer process instead of being 250 nanometer process or something like this. So none. I wish it would have been easier, but more difficult, but no. No? Are they happy? Did they learn something? So ask people again, who is going to start doing FPGA design now? Nice. Okay, great. After that, you'll have to find the parts. Well, buy an eval board. They've already been made, so they're easy to find. All right. I'm glad if I got a bunch of new disciple in the group of FPGA designers. Yep. No, Sunday, yes, the big reveal, and yes, thank you. Well, the next talk will be 2 parts. The next talk will be a bit of a repeat what I did at VCS West, which is really the process of designing a product from scratch and the hurdle and the pain and suffering that one needs to endure to actually make it happen, which is part of my suffering. So I'm sharing the suffering because I figured out over the years that some people kind of brush off the idea, oh, it's easy to make, and they complain, and I'm trying to share the pain with everybody. But also it's going to be the moment I'm going to unveil, because I've been designing this keyboard version of the Phoenix with a 68040, the A2560K, and I'm finally going to be unveiling to the world, and it's going to start, I'm going to do it at this moment, at the end of the presentation. So that's why I'm really grateful that you gave me like 30 more minutes. And that's what I'm going to talk about and show. And I'm really thankful. Thank you very much to everybody for assisting. I really appreciate it. And Jeffrey, I'll see you on Sunday. Bye guys. Bye everybody. Thanks.